Okay, so it's going to be broadcasted again, and we do it as yesterday. Good morning, everybody. This morning we talk about bone remodeling, and I will give this presentation also on behalf of my colleague Jasper Homminga, who helped me to generate this presentation. Yesterday we already looked at bone, but if you take an X-ray, you see these trabecular structures very nicely aligned, and it must have to do something with the load that is applied on the bone and transferred through the bone. Our bone is very smart, and therefore its structure is optimized. Not only in long bones, but also in the trabecular, in the vertebrae. You can see here the alignment, and you can see in red the stresses, and you can see that the trabecular structure is also optimized in the vertebra, in the cancellous structure of the vertebra. So there must be a relation between form and function. And Galilei in 1638 already noticed that there must be a relationship between the bone and the size, and especially the weight of the person or of the species. So size of a bone must be related to the weight of the animal rather than its size. Weight is more important than size. So if we have a light-weighted animal or a heavy-weighted animal, the bone will adapt its strength and its size. In the 19th century, an anatomist, von Meyer, worked together with an engineer, Kuhlmann. And Kuhlmann generated cranes and other mechanical engineering devices. And this is a cane. So this is Kuhlmann's cane. And he calculated the strength of just a cane. And then he worked together with an anatomist, and the anatomist saw a resemblance. And that's how, let's say, this form and function relationship came along. Later on, Julius Wolff said that bone must adapt to load. So the bone is optimized to its load, but if you change its load, it will adapt. So the structure will probably adapt. And we now call that Wolff's law. So Wolff's law means if you load bone, it will densify. If you unload bone, it will go away. It will adapt. Wolff's law. And he saw Wolff learned himself by looking at fractures, how after a fracture the bone would deform and then it would adapt to the new situation. So he looked very carefully to fractured bones. In 1987 there was a very famous experiment of a turkey experiment, and the turkey had his leg basically in a device. Here you can see that. So the turkey is still alive, and with that device they could apply different loads, okay, while the turkey was living. Here you see an in vitro situation of that, an experimental. So they could grab hold of the bone of the turkey, and then they could load it heavier or less heavy, and then the bone would adapt to that. And here you can see two of the results. So this is a cross-section of that bone in the unloaded situation, and of the loaded situation. And you can see in the loaded situation, you can see that there is more bone formation. And this also happens in athletes, for example, in tennis players. Tennis players have a very strong bones, not only the muscles, they also adapt, but also the bones. Okay, in 1885, Roux said, well, okay, maybe bone adapts, but how does it do it? It has to do something with bone cells. There must be cells feeling that there is a high stress level. And that's why bone can adapt. So cells in bone regulate bone remodeling because our whole body consists of cells, so there must be something that regulates bone remodeling. And there are a number of cells that are then important. We have the osteoclasts, and osteoclasts, they eat bone, they remove bone. Okay? Osteoblasts, they make bone. These are the bone makers. And osteocytes, they can feel stress, as I indicated yesterday already. Okay? And here you can see again an osteonic system from above, like we already discussed yesterday. And you can see here the caniculi again and the osteocytes. Okay? These are the osteocytes. And in the osteocytes and the osteoblasts, the osteoblasts, when they are not doing anything, so osteoblasts are bone makers. If they are on the outside of the bone, they don't do anything, and they are called lining cells. So basically, they are waiting to become active. In 1966, Frost came with the theory that there is bone remodeling and bone modeling. And remodeling is just maintenance. It is bone removal and bone addition in the same speed. So there is no bone turnover. I mean, there is turnover, but there is no gain or loss. Modeling means that there is either removal or deposition. Okay? So how does it work? Well, if you have a piece of bone and the osteoclasts do their work, they eat away the bone, okay? Because osteoclasts are the bone eaters. So the bone, this cavity has been made, and the osteoblasts will regenerate bone. So these are the osteoblasts, and here there is new bone formation, which is called osteoids. And this is osteoid. So this is new bone, fresh bone. So basically, the osteoclasts make a tunnel by eating bone away. The osteoblasts will follow and lay down new bone. Okay, and in that sense, you have new bone. So if there are fractures, for example, small fractures, the osteoclasts eat away bone around that fracture, small fractures, and the osteoblasts lay down new bone, and then the fracture, those microfractures have been resolved by the osteoblasts. And this is basically how it goes up and down and by bone remodeling. This is bone remodeling. Okay, Roden in 1966 indicated that this is also governed by hormones. And he also indicated that from the literature, it is clear that mechanical strain must be a factor that governs bone resorption or bone formation. So there are hormones involved, but also mechanical stimuli. Okay. The hormonal environment, we know that from women in the menopause, after the menopause. We know that bone resorbs, and older women have a high chance of getting osteoporosis. So that's a hormonal thing. So we look as engineers to the strain field and how that affects then bone turnover. So you can apply a certain load on a bone here, and the osteocytes, they feel the strain. And then if the strain is high or low, they will activate the osteoclast. And the osteoclast will eat away the bone. And then the osteoblasts, they feel, and they get a signal from the osteocytes, and they make new bone. And this is then how bone remodeling is taking place. And if you change the loads, it will go in different speeds and with different magnitudes. Okay? So you can make a kind of a control loop of this. So we have the architecture. So this is, for example, this is a micro CT scan picture. You have a micro architecture. You can apply the load. So locally there are stresses and strains. And the osteocytes, they feel the strains, okay? And they turn on the osteoclasts and the osteoblasts. And which either of them is more active, so it's a plus or a minus. If the osteoclasts are more active, then there is bone resorption and it's more osteoporotic. If the osteoblasts are more active, it's going to densify. If this is more dense, it will change the stress field, or the strain field, and the osteocytes feel a different signal. And if it's very dense, the stresses will be lower, and then the osteoclasts are asked to do something because the stresses are relatively high, low. Okay, so this is how remodeling takes place. Now there are many unclear issues. For example, are osteoblasts and osteoclasts both controlled, or is only one controlled? Do osteoclasts always precede osteoblasts? So first bone is removed and then there is bone addition. And what is exactly the driving signal? I told you yesterday that it might be the fluid flow in the caniculi. Maybe it's just a theory, we don't know for sure. And what is the role of these lining cells that are waiting, you know, the osteoblast lining cells that are waiting to do something? What is exactly their role? So there are many things that we do not know yet. But from an engineering point of view, I think we are quite successful in simulating the bone remodeling, and because the outcomes of our simulations are coherent with what we see in vivo. Okay, I show you now a video of osteoblasts and osteoclasts, how they act. It is with sound.
The skeleton changes across the human lifespan. This is characterized predominantly by bone formation and growth throughout childhood, followed by a gradual loss of bone density that begins in early adulthood that can accelerate significantly in older adults. The density of bone is modulated by a group of cells including osteoclasts, which are multinucleated cells that resorb bone, and osteoblasts, which refill the resorption cavities created by osteoclasts. Osteoclasts anchor themselves to the surface of bone. This creates a microenvironment underneath the cell, which is referred to as the sealed zone. Within this zone, the osteoclasts create an acidic environment that dissolves the bone's mineral content. Once the mineral content of the bone has been dissolved, enzymes released from osteoclasts remove the remaining collagenous bone matrix to complete the process of resorption. Following resorption, osteoblasts move into the resorption space and start to produce and deposit organic matrix called osteoid. Osteoid, a substance made predominantly of collagen, forms a scaffold in which minerals including calcium and phosphate begin to crystallize. Some active osteoblasts become trapped within the matrix they secrete and thereby become osteocytes. Other osteoblasts will undergo apoptosis or will revert back to lining cells which cover the surface of bone. This cycle of bone resorption and formation is referred to as remodeling. There is also a process where bone formation by osteoblasts occur without prior bone resorption by osteoclasts. This results in an increase in bone mass and is referred to as bone modeling. Bone modeling promotes the growth of bones and is important for maintaining bone strength. Remodeling also plays an important role during bone growth by optimizing the growing structure. After the age of 30, most people experience a gradual loss in bone mass due to a relative decrease in the activity of osteoblasts compared with osteoclasts. However, there are many factors that impact the process of bone remodeling and influence the degree of bone loss we experience as we age. For example, medications such as glucocorticoids, which can promote osteoclast activity and also reduce bone formation. Proper nutrition and physical activity can help strengthen bone. It is also believed that osteocytes form a complex network in bone that can sense any increased workload on the bone and respond by triggering the differentiation and activity of osteoblasts to increase bone density. Conversely, when bone experiences reduced loading conditions, such as during long-term bed rest, resorption and remodeling increase to eliminate underloaded bone. Loss of bone mass reduces its strength and increases the risk of fracture. This highlights the importance of staying active, maintaining good nutrition throughout life, and being aware of personal risk factors associated with low bone density.
Okay. As an engineer, you can look at bone remodeling problems. And for example, we can assess what happens around a prosthesis with the bone. We can also assess what happens if what happens with osteoporosis, if people get osteoporosis, and how high the fracture risk is. So this is a typical neck fracture of an osteoporotic patient. It's very well known that vertebrae get very weak in people who have osteoporosis. And that's a big problem because the Western population is aging, so people getting older, but the bone maintenance is really then becoming a problem. Also with prosthetic teeth, so if you have an artificial teeth, it's unloaded and it's very loaded in a very different way, and then the bone will adapt. So if we look at engineering problems, I showed you this scheme already. And what we do if we look at a bone, we make a finite element model that I showed you yesterday. So you can calculate the stresses and strains. And we can do that in a treated bone, and we can do that in a control bone. I will show you in a minute how that works. So you calculate in the normal bone the stresses and strains. You calculate the stresses and strains in a bone around a prosthesis, for example. So you get strains at a certain location. You get a strain at the same location around an implant, and then you compare it, and then the difference you put in an adaptation rule. Okay, this will become clearer in a minute. The adaptation rule will then predict what happens with the density of the bone, whether it will increase or decrease its density. Okay, to explain that, you can see here the stress transfer in a femur. So it's loaded, and you can see how the stresses are transferred to the cortices. If you put in a metal implant, which is quite stiff, the load will be carried by the implant and only transferred in this direction, in this area. This part of the bone doesn't feel any loads anymore because there is such a stiff implant in it. And that's called stress shielding. So the metal implant shields the bone from stress. That's why it's called stress shielding. If we do a calculation on that, you can see it here. So this is the stress or strain energy density, which is basically stresses or strains. It doesn't matter so much. You can see here high stresses. If you put in a metal implant, you can see that the stresses are contained within the implant. Okay, so here, if you compare this area with this area, the bone doesn't feel the stress it felt in the intact case, right? So stresses are much lower, stress shielding. So it means that the stresses are lower, and we then can put that in an adaptation rule. And if the stress level is normal, there will be no gain or loss of bone. But if it's lower, it will lead to a loss of bone. And if it's higher, the stress level, it will result in a gain of bone. Okay? And that happens also if you do heavy activities or if you go into space, the same phenomena will happen. So the same phenomena as space or heavy activity will happen around an implant, but then on a local level around that implant. Okay, so we do a site-to-site specific comparison, and we put it in this rule, and we calculate whether there is bone loss or bone gain. Okay, that is a bone remodeling simulation. Now, at our laboratory, and Professor Huiskes has kind of initiated this. We have done a lot of work on that, and I'm going to show you some animal experiments and animal simulations of Bert van Rietbergen. He published that. So these are dog experiments executed in Chicago. And here you can see some results. So what you see then, this is an implant, and this is the contralateral side. You can see that there is densification of the bone directly around the implant relative to here. Okay, so you see that the bone becomes denser around the implant here, especially at the corners. And that's because of the high stress at the corners, for example, around the implant. But what you can also see is that here it's thinner. The cortex is thinner here relative to here. It's thinner here relative to here. Okay, so there is adaptation directly around the implant, but also on the cortex. So it's cortical thinning. If we made a model of that, and this is a very coarse model, this is already 25 years ago. If we made a model of that, we can see that relative to this trabecular density, we see more densification here around the implant, especially at the corners. Okay, and we see that the cortex is thinner relative to here. So we found exactly the same phenomena in our animal simulations. So that's bone adaptation. Okay. So how do you measure periprosthetic bone adaptation in vivo? And here you see an X-ray example. So here you can see that the bone is lost again. And basically for most patients, this is not a big problem, because if the bone is not needed, it might as well go away, and the fixation is not jeopardized. It is only when a patient then falls and the load is coming from a very different direction, it could break out. And if the surgeon has to revise the component, he is confronted with a lot of bone loss, and he cannot fixate a new implant anymore. So it's really more a problem if a person falls and needs a revision, than in general daily functioning. Okay, so you can measure the density of bone by a DEXA scan. And a DEXA scan is a dual energy X-ray absorptiometry. So it's basically one X-ray, but then double. An X-ray gives you a picture, and if you do a double with different energy levels, you can quantify the amount of calcium which is in the body. It's kind of like a CT scan, but then without artifacts, because if you make a CT scan, usually you have artifacts because of the metal. Okay, so this is then how it looks like. Yeah, so you have an implant and you have bone around it, and typically around the femoral implant we have 7 zones. And Dr. Gruen from the US proposed to make this division. So we have 7 Gruen zones, and it starts on the lateral side, 1, 2, 3. On the bottom of the implant, we have zone 4, and we have 5, 6, 7 is on the top. So 1 and top, okay? These are the Gruen zones. And the size depends on the length of the stem. So they are related to the stem. Okay? So in terms of stress shielding, we expect the most stress shielding in zone 7, because the load is transferred distally, and zone 7 is always where we see the most bone resorption. Zone 7, you can see that also here on the X-ray. You can see here the division of the Gruen zones. Zone 7, we see a lot of bone loss here, so we will quantify that with a DEXA scan. Okay? So you can measure the bone mineral contents, the area, and then the grams per square millimeter or square centimeter bone. So it gives you not a volumetric measurement, but a surface measurement, because the DEXA scan is just a surface and not a volumetric measurement. Okay, so then you can have measurements. And this is Gruen zone 7 of an implanted femur. This is a contralateral side. So you could have a loss of bone of 46% in Gruen zone 7, and then a little bit less loss distally. And you could even have bone addition. And that typically occurs around the tip, because there is a high stress sometimes at the tip of the stem, and then the bone will respond to that by adding bone. Yeah, so that is, we see that quite often. But a lot of bone loss on the proximal side, you see that here. Okay? Okay, so we can do some simulations, and this is one result of a simulation being published by Harry Wijnands. So this is an implant in a bone, and this is the initial bone mineral density in our simulations. And this is a cemented component. I see here the metal component, and this is the cement, okay? And this is made of cobalt chrome. And we see a bone loss of 38% in Gruen zone 7. It's a lot, huh? If you make the component of titanium, it is changed. You see less bone resorption. This is due to the fact that cobalt chrome is much stiffer. It's 200 gigapascals than titanium. It's about 100 gigapascals. Okay, so if you put something in which is more flexible, it looks more like bone. Okay, so the more flexible it is, or more similar to bone, the better it is in terms of bone turnover. Okay, yeah. So this is how we can calculate the bone resorption. Okay, so to make it maybe even more complicated, I have this graph. So what we see here is we see cemented components and uncemented components. Okay, what you see is here the bone loss in Gruen zone 7 for cemented components and uncemented components. We see for the uncemented components a lot of bone loss. You see that? And this is due to the fact that uncemented components are bigger. So if you have an uncemented component, the diameter needs to fill the cavity. Okay, so it's bigger. So I have here, for example, a cementless component. And this is a cemented component. This one is typically smaller, hence more flexible, because there needs to be a cement layer around it to fixate the stem. So this is a cement layer which is quite flexible. So this one fills the whole cavity, which is really bulky, very stiff, therefore there is more stress shielding. Okay? Okay, so uncemented components typically have more problems in terms of bone resorption. Okay, then you could say, okay, let's make a theoretical implant which is called isoelastic. Isoelastic means I make an implant which is as stiff as bone. So I put in a piece of bone as a replacement. Okay, then the bone loss is indeed much less. Okay, and there have been components on the market that are isoelastic. In fact, I have one here. So this is an isoelastic implant. So the stiffness, this stiffness would be exactly the same as bone. Okay, it's called isoelastic. The problem, and so you can see here the phrase use it or lose it. So that means use bone, stress bone, or you lose bone. Okay, so that's the selling argument of isoelastic stems. The problem, however, with these isoelastic stems, which are, I don't think, on the market anymore, is that they have a problem with fixation. So this is a very complex picture, but it shows the interface stresses, because you can imagine if the load is transferred to the bone on the proximal side, which we would like, because then the bone is stressed, you need to also transfer a lot of loads on the proximal side. And you can see that here, this peak here, is the transfer of load for an isoelastic stem. So it means that the stress transfer on the proximal side is huge, and basically the interface cannot cope with that. So it will not grow, it will not fixate itself, because there is too much flexibility. So the loads are too high there. So the interface will fail. So the idea is good, but it turns out that it doesn't work well enough. Okay? Okay, then in a simulation, you can play around with coatings as well. So this implant that I showed you here has a fully coated implant. You could imagine if I only coat the proximal part, let's say this part, and the bone grows into this part, there is stress transfer on the proximal side, less here because there is no ingrowth. So the stresses are distributed here. It's better for the bone because there is less stress shielding. Okay. Of course, if it's too small, the stresses will be too high, like the isoelastic stem. So there is a balance to be made. Okay. Okay. So you can imagine if I look at bone loss in groove zone 7, this is the proximal medial zone. If you have a fully coated or a partly coated, which is this case, the partly coated one transfers more load proximally. And if you have D, which is here, you transfer more load. And if you have a very small coating, you transfer a lot of load and less stress shielding. You can imagine this, the ingrowth in this small bit is at risk. So that will not happen. Okay, so this might be the best. Partly coated, which is this one, but in reality that doesn't work. So companies more opt for this one. So here you can see an example of a proximally coated implant. This is a typically what we see, because it reduces stress shielding, and in addition you have to realize that I have here the fully coated implant, and the surgeon just hammers it in the bone. And it can grow very, the bone fixates here and perhaps here. And in some cases, maybe especially on the distal side, if the surgeon then has to remove it because of an infection, for example, it's very difficult to reach that part distally. So what he then typically does is he has to make a big cut in the bone, opens it up, and then removes the implant. So it's very difficult to remove if a prosthesis is fixed at the distal side and the distal tip. And that's also an advantage of having the coating only proximally, because then he can put the scissors into the interface and he can loosen the implant. But he cannot reach the tip, because then he has to split the femur, which is of course not what we want. Okay, so proximally coated implants are easier to remove. But of course, there is do they have enough surface for ingrowth? That is always the balance that we look for, and us as engineers can do optimizations for that. So we can see how we can make a robust system. This is an example of a study that we did. So you can imagine that you could have an implant that has different layers. So the center could consist of another material than the outside, for example. And we can play with that to optimize or minimize stress shielding. Okay, and we use this algorithm to see the effect on bone resorption. The first thing we do is to use, in our bone remodeling simulation, is to use in vivo data. So what we do is we take, let's say we take an implant, apply this remodeling simulation, and then we know from the clinic, from clinical reality, how much bone resorption there is. So what the bone mineral contents is after 2 years. So that is this dotted line. Okay, so because we can measure that with a DEXA scanner. Now, subsequently, we do the simulation. And depending on the parameters here in the bone adaptation, we can get curves of bone loss. Okay, so I look at now Gruen zone 7, and depending on the lazy zone, this is called the lazy zone because it is an area that I consider normal. So let's say the stress here is 3 megapascal in the bone. Okay, if it's 4 megapascal, I assume that there is no effect yet. If it's 5 megapascal, there is bone adaptation. Okay, so that means that the lazy zone is then 2. Maybe in some circumstances it could be 3 or 4. We don't know. It depends on the settings of this scheme. So I can make this lazy zone bigger or smaller. I can make the bone more lazy or not. That's why it's called the lazy zone. Okay. So if I make the lazy zone, or it's also called the dead zone, smaller, if I make it very small, so I make it very small, it means that the bone is very reactive, okay? It means that I lose a lot of bone very quickly. If I make the dead zone very big, I make this bigger, it means that I need to have a bigger change in stress before something happens. And that's why I don't lose, in this case, the dead zone is 0.75, I don't lose a lot of bone. Do you understand that? It's very difficult. But so what we do, basically, to summarize, is I'm looking for the lazy zone that predicts the bone loss, what we see in the clinic. So I know that if I choose a lazy zone of 0.55, I have to look at 100 or 200 computer time units. That gives me the exact same loss of bone that I see in the clinic. If I use a dead zone of 0.35 here, I have to look at 50 computer time units, because it's in my simulation it's more reactive. If I use a dead zone of 0.75, I will never find a result that is according to the clinic, because my simulation is not reactive enough. Okay? Okay, so then we applied the 0.35 and 0.55 lazy dead zones, and then we simulate that clinical case, and we see here the bone loss or bone apposition in the 7 Gruen zones, and this is the clinical case, yeah, the clinical values, and this is our simulation. And so this is how we fit our computer parameters to the clinical case. Okay? So I know now I have a reliable simulation, and then I can play around with my design. So the epoch stem is the stem that we simulated as a clinical case, and now I design something else. Okay, so it means now that if I simulate a titanium implant, which is stiffer than an epoch stem, epoch is kind of made of a flexible material. In Gruen zone 7, I predict a lot of bone loss, more than the epoch stem. And the epoch stem is now marketed by Zimmer, which is a company. And it's made of PEEK, of PEEK. It's a plastic material. But they want to have something of tantalum, okay? So we made a component made of tantalum with a solid core and tantalum porous structure on the outside, which gives exactly the same bone resorption as that epoch stem. You can see that here. Okay, so first in the simulation, we fit our parameters with clinical data, and then we apply that to design a new implant. Because if we start designing a new implant without knowing the clinical relevance, we're just playing with computer games. You know, we don't know what the clinical relevance is. Okay, so in this case, we were able to design something which behaves exactly like the epoch. And the Zimmer company is now considering whether they're going to make this implant. Okay? One last issue is bone remodeling depends on the stiffness of the implant I showed you before. But it's a relative stiffness to the bone. So it means that if you have, in this case, if you have very bad bone, you know, osteoporotic bone, you will lose a lot of bone very quickly. Because if you have an osteoporotic bone, the same implant looks much stiffer than if you have very good bone. If you have very good bone, a very stiff bone, this implant looks more flexible relative to than if you have osteoporotic bone, because then the same implant behaves much more stiff. So let's say in elderly women who already do not have a very good bone quality, if you put in an implant, they will also suffer extra if you put in the implant, because the stress shielding effect will be even bigger for them. Okay? So that is also something to keep in mind. So the patients are also very different, and that's why it's very interesting and wise to include also sensitivity analysis to bone quality in your simulations. Okay? Okay, thank you very much. Sorry?
The body is known to reject any particles. So
Sorry, I can't hear you.
the body is always known to reject any foreign particles. So, like, what is the percentage of successful place in this foreign implants, metallic implants?
I come back to that. Good morning. Next presentation is about biomechanics of cartilage. And of course, cartilage, we have cartilage in the body at many different places. You can see hyaline cartilage, which is also in our joints. You can see it's also in the lungs, the nose, the joints. Yeah. Elastin cartilage is in the ear, for example. And we have fibrocartilage close to the os pubis, for example, that we discussed yesterday. Okay, so cartilage we have at different sites. The cartilage I'm talking about is the cartilage on the joints. And typically this is the structure, so this is the site of the joint. And at that joint we have collagen fibers oriented parallel to the direction of gliding. Okay. Here you can see the cartilage cells, the chondrocytes. Yeah, so these are round cells. And of course we can have a fissure in the cartilage. So here you have the joint space and we have a fissure in the cartilage. That's not good news. Why is it not good news? It is not good news because the cartilage has no vascularization. So that means that it cannot heal itself. If you have a fracture in the bone, if it's stable, the bone can deal with that. Cartilage cannot repair itself. Also, the cartilage doesn't have any nerves, so you do not feel whether there is any problem until it locks your knee or it's more painful on the bone side, but not the cartilage itself. You cannot feel that. Okay, so here you have a knee of a mouse. This is a mouse, and it's bended in 90 degrees. Okay, so it's bended like this. Okay, and we make a picture from this side. So the tibia you see from the frontal side, so cross-sectional frontal side, and the femur is cut like this. Okay, and we see in red the cartilage. So you can see here the joint cartilage here. Okay, here and here. This is the meniscus. Yeah, you see a piece of the meniscus here as well. And you can see here something, which is also cartilage apparently. And that's the growth plate. Okay, So I told you yesterday, from this growth plate, from the cartilage, ossification takes place. So that's how the mouse bone can grow. Okay, you can see here also on top, this is also articular cartilage, because on top of here there is the patella, okay, the kneecap. So here is also the cartilage. Here you can see it better. So this is the kneecap and the patella with cartilage articulating in the groove of the femur in this 90 degrees projection. This is an osteoarthritic mouse knee. So we injected collagenase, and collagenase has the property that it resorbs or resorbs cartilage. So you can see here that we lost cartilage. And you can imagine that we can use this mouse model to do all kinds of research projects on how to regenerate cartilage or how to maintain stability or develop medications. Okay? The function of cartilage is, of course, to spread the load over the joint so that we don't get peak stresses that could be painful. And it lubricates the joint. And cartilage consists mostly of water. Very interesting material, huh? And the solid matrix consists of collagen fibers, proteoglycans, and chondrocytes, the round cells that I just showed you. Those are chondrocytes, cartilage cells. But they consist of only 2% of the matrix. So there are very, you know, the volume of the chondrocytes is very small, but they are super important. Okay? Now here you see the joint space, okay? And you see this is the water content. So we have 85% of water at the surface of the joint. 85% of water. That's very important because if I load the cartilage, I squeeze out that water, which lubricates the joint. Okay, so I need a lot of water at the surface. If I go in, the water content is reduced. So it's again very optimized for its function. The collagen concentration, we need very strong collagen at the top to resist the shearing stresses. So we also have a lot of collagen at the top. If you go deeper, there is less collagen. If you go deeper, it's becoming more ossification, and there is more calcium then. Okay. Now basically, the cartilage is you can think of it as a very smart sponge. You know, a sponge with water, you know. So if you compress it, you force the water out. And if you force the water out, it lubricates itself. And the cartilage is a very smart sponge. So here you can see that if I load it in this direction, I squeeze out the water, which basically pushes the parts apart. Okay, so it lubricates and also pushes the joint from each other, so there is less wear and tear. Okay. Now, one important aspect of cartilage are the proteoglycans, and the proteoglycans are molecules, and they have glycosaminoglycane and hyaluronic acid. And these proteoglycans are woven together with the collagens. Okay, so the proteoglycans are woven with the collagens, and the proteoglycans, they take up water. So if they take up water, they increase the size, and therefore they boost up the collagen fibers. So they pre-stress the collagen. Okay. So the proteoglycans, the GAGs, the glycosaminoglycane of the proteoglycans are negatively charged and therefore attract salts. and the salts attract water because of osmosis. Okay, so the proteoglycans therefore are charged with water, and therefore they pre-stress the collagen fibers. And because of the pre-stress of the collagen fibers, if you load it then, the collagen fibers feel, they pre-stress, and so there is a kind of a balance of load. So it's even smarter than just a sponge. It's a preloaded sponge, okay? Because the collagen fibers are then under tension. Treatment of cartilage defects. How do we do that? Well, you can do an arthroscopic assessment of the knee, like we saw yesterday in the movie. It's a relatively small operation. It's minimal invasive through a small number of portholes. And the surgeon will try to readjust the cartilage by removal of the loosened bits. They don't repair the cartilage. And sometimes it only has a short period effect, because if the damage is too large, the people will generate maybe osteoarthritis. Okay, so it's not, you know, it's sometimes a short solution. Okay, this is a movie without sound. So this is an arthroscopic assessment. You can see the loose bits of the cartilage. And you also have to realize that a lot of us have cartilage bits that are loose, but it's not a problem. You know, so you can survive and you don't feel cartilage damage for a long time. But if these loose bits get in the way, then you need to do something about it, because it's very painful. You can see how rough this goes, huh? It is not a very delicate, you know, it's big. Big chunks of cartilage are removed. This is then a shaver. So there is a rotating, it rotates at the end of the tip to make it very smooth. The objective is to make a smooth surface. So it's not a repair, it's just to get rid of the problem. Okay, so another way of dealing with cartilage defects is a mosaic transfer. So this is not very popular, but people are working on it to improve it. So what they do is, so there is a cartilage defect here, and what they do is they take punches of cartilage in an area that is not used. So these are punches, so pillars of small bone with cartilage, and they transfer it to the side of the mosaic plastic. So this is the defect. So it needed 5 pillars, and these 5 pillars come from here. I'm not sure. I see 6 pillars, but apparently something went wrong with 1 pillar. So this then is supposed to regenerate and solve the problem. And there is a lot of debate amongst surgeons whether this is a good solution, because maybe you repair it here, but you generate a new problem here. And how do you know that this is not really used, because there is cartilage here, and the body would not generate cartilage here if it would never be used. So the success rate of this is, let's say, debatable. We've done studies on this. So this is a goat femur. So this is the groove of the femur. In a goat, it's much more V-shaped. And we have here a defect, and we're going to implant 2 pillars. Okay. So you can see how it goes in now. And but here you can see the problem with the pillars. So this is one pillar, this is the other pillar. It's very difficult to get it really very smooth. Because you can imagine that this edge is not optimal. So it's very difficult to get it really very smooth in the mosaic plastic. Here you can see it in a patient. So this is an MRI scan of a patient. So they also had 2 pillars. And this is then the site where they removed it from. And they are going to follow up this patient. Okay. And typically what happens if this would happen, there will be some fibrous tissue generated to fill this gap. So it's not as bad as this looks, but it will not be really cartilage, of course. Okay, so that the cartilage consists for maybe 70% out of water, and that has consequences for the mechanical properties. Okay, so that's why I'm going to explain a little bit about biphasic materials. So cartilage consists of water and a solid material. So it consists of 2 different materials, and that's called biphasic materials. So yesterday, Professor Gupta already talked about stresses and strains, and I'm going to repeat a little bit of that. So if you have a piece of material and you're going to pull on it, and you have a certain surface, the stress on that surface is the force divided by the area. Okay, that is simple, I think. The unit of that is Newton per square meter, or Pascal. Okay. If it elongates, of course, and then there is this strain. The strain, indicated by epsilon, is the difference in length divided by the original length. Okay. And the unit of strain is meter divided by meter, so it's unitless. Okay. So people talk about 0.01 strain, and you don't have to have a unit, 0.01, that can be the case. Or they also say 1%. That's also 0.01. So pay attention whether they mention percent of 0.01 as the value. Okay, so Hooke's law is the relationship between the stress applied and the strain obtained. And so it's the division. So if you divide stress by strain, the unit of elasticity, the elastic modulus, is still Newton per square meter. So an elastic modulus, something with an elasticity, is indicated in the same way as stress, which is a bit strange, maybe, but that's the case. Okay, so this is also Newton per square meter. This graph is already something that we saw. So if you have a stress-strain curve, if you put on more stress, it will strain more. And if it's linear, like the spring example of yesterday, then it becomes elastic. It's reversible. Oh. But suddenly, at some stage, you pull too far, and the material becomes plastic. It's yielding, they say. So this is the yield strength, and it's going to yield, and then it is irreversible because there will be, it's not elastic anymore. It's irreversible, and you come into the non-elastic area. Okay? So this could be the curve for bone. So this is then under compression. This is a typical bone curve. If you have collagen and you pull on it, you can only pull on it. First, you have the fibers that all are oriented in the same direction. Then there is a certain stiffness, and then the collagen fibers start to snap one by one. And it becomes weaker, weaker, weaker until it completely snaps. Okay? So this could be still the elastic area, and here it becomes the non-linear. So cartilage has two phases, the solid phase, let's say the collagen and the proteoglycans, and the fluid phase. So it's a biphasic model, and therefore it's important to look at a linear elastic modulus or material versus a viscoelastic material. A linear elastic material, its deformation is not depending on time, like a metal, like a bridge, for example. If the bridge is hanging, on two sides, metal bridge, nothing will happen. If you would make that of a viscoelastic material, the bridge would gradually deform until it is in the river. Don't do that. So viscoelasticity is that the deformation is depending on time, and the biphasic material does that, such as cartilage, ligaments, and basically all materials in the body to some extent. Even bone is a little bit biphasic, but we often ignore that. Okay? So if I apply a certain strain to a linear elastic material, like a metal, in time there is no change. Okay? If I apply a certain stress to cartilage, if I load cartilage, it will gradually deform. Okay, so it will gradually deform, so the strain will become higher. That is basically because I load it and I squeeze out all the water. So I start loading it, and then the water is still there, and it takes just time to get the water out, and that's why there is time dependency. Okay, so that has also consequences for creep and relaxation, because that is also terms that have to do with time-dependent properties. So if I apply a load to something, so I apply a constant load to something, it will creep. So time-dependent deformation on a constant load is called creep. Creep is something that deforms. So this is what people, what you know, what you can imagine. Stress relaxation is a little bit the same, but then a little bit reversed. So if I apply a certain strain, then the stress I need initially is much higher than later on. So for example, I have a cartilage layer and I force it to deform 50%. I need a lot of power for that because the water is in the way. If I wait for some time, the water is moved away and I don't need any force anymore. And so the force is reducing, the stress level is reducing for that. Okay? Okay, so the material parameters to describe a biphasic behavior is stiffness of the solid matrix, and it's not exactly as the elastic modulus, but we call it the aggregate modulus, H, but it's similar to the elastic modulus. Okay, that is of the solid phase. We have a Poisson ratio, which is very similar to what we have in materials, and basically it means if I apply a load in this direction of deformation, how much does it then move in the other directions? And if you imagine water in a balloon, let's say you have a balloon, you blow up a balloon, you put in water, and you squeeze it 1 centimeter, it has to go somewhere. The water needs to go somewhere. And it means basically that in this side it will go half a centimeter, and in this side a half a centimeter, because the volume remains exactly the same, because it's water. So this, I move this 1 centimeter, and this extends half a centimeter. We call that the Poisson ratio. Poisson ratio of water is 0.5. It's incompressible. So that's why it says here 0.5. For bone, for example, if you compress bone, it also becomes a little bit wider, but it's in the order of 0.3 or so, usually. So incompressibility is 0.5. Okay, so that is a character of water. But in addition, of course, it is important to know the permeability, because if it's super permeable, the water will be squeezed out very quickly. If it's not permeable, it will stay there for a very long time. So permeability is very important. And in soil mechanics, you can imagine it is very similar in sand and water, and how mud is basically behaving. So the theories we use for cartilage comes from soil mechanics. And there is Mr. Darcy, he basically designed experiments to assess properties. So suppose we have water here, okay, and we have a rigid filter here, and we have some cartilage in between, okay, cartilage in between. And we have a fluid flow because we have a pressure gradient. So there is high pressure here, lower pressure here. So there is a pressure gradient. The water goes through the cartilage, okay? And the amount of water per second that goes through the cartilage is depending on the permeability. If it's very permeable, there is more water going through. If the surface is bigger, there is more water going through. If the pressure gradient is bigger, there is more water going through. But if the height of the cartilage is bigger, it's more difficult, so there is less water going through. So this is Darcy's law. Okay? So in that respect, you can also describe the permeability as this function. Okay? So that is why we can measure the permeability of cartilage. And you can assess then the quality of cartilage. Okay? Of course, this was fluid flow due to a pressure, but what about loading? So if you have the same structure, then you can measure the amount of fluid that has come out of the cartilage. Okay, and this is, of course, what happens in joints. So you can have a load on a joint, and basically you generate, or the water generates intra-articular contact stresses and pressures by squeezing out the water. Okay? And depending on the joint and the congruity, a joint can be more or less effective to keep the water inside the joint. So a hip joint, for example, the cartilage matches very nicely from the femur to the acetabulum, and the water has no way to escape. It cannot, where does it have to go? So that is a very congruent joint. In a knee joint, if you look at this joint, the menisci are removed, you can imagine that the water can be squeezed out very quickly. Okay? So to contain the water into the cartilage, you need very good congruency, because then the water cannot escape. So you can have a more congruent joint or a less congruent joint. Okay? So here you would have a very high contact area, and here a low contact area with a high contact stress. And also the water has a big chance to escape. So here you will have a little fluid flow, and here in this case you will have high fluid flow because the contact stress is high and also the fluid can escape easily. Okay, so the way we can calculate the stress levels on the cartilage is, for example, doing finite element analysis. Okay, so we can simulate a knee joint and we can remove, for example, the meniscus. Because in the previous picture, this looks like a knee without the menisci. So because usually here is the meniscus, so then you increase the conformity of the joint. Okay. And people have so you can do all kinds of calculations on the contact stresses. And here you can see an example of the contact stresses if you have a native meniscus. But if you remove the meniscus on this medial side, you can see that there are very high contact stresses. Yeah? And these very high contact stresses will damage the cartilage because the high contact stress will squeeze out the water. And basically you're not walking on water anymore, but you're walking on the collagen fibers. And the collagen fibers cannot resist that for a very long time. Okay? People test cartilage with Darcy's law, but also in different, in other ways. And they call that unconfined compression test, confined compression tests, or indentation tests. So you can have an unconfined compression test if you have a piece of cartilage here and you compress it, okay? And the water can just disappear on the sides. Okay, the confined compression test means that you lock up basically the cartilage, so it cannot escape on the side, but you have a permeable filter on the top, so you can only squeeze out the water in this direction and not on the side direction. This is a confined compression test. And people also do indentation tests because then they can assess multiple locations in the cartilage and they can assess the difference in mechanical behavior everywhere. Okay, it's like the nano indentation test we talked about yesterday, but this is a very local assessment. Okay, so in the confined compression test, basically the water stays, let's say, in the cartilage, and the matrix takes up 20% of the load, and the water takes up 80% of the load. Okay, so this is basically you load on water. In an unconfined compression test, the water can just escape very easily. Okay, so initially you load the solid matrix for 20%. But in time, when the water is all away, all the load is on the matrix because the water is flowing out. Okay? So at the beginning here, you have all kinds of fluid flow because the fluid is just disappearing. But this is an unconfined compression test. So if you have a very good congruent and closed, I would say almost closed joint, there is no fluid flow and it looks like a confined compression test. You know, so the fluid stays there and it's protecting the collagen. If you have an incongruent joint, the water can just disappear. So you have a loss of water due to the flow of the water. It's like an unconfined compression test because and then the load will be on the collagen. So if you have incongruent contact, like meniscectomy after a removal of the menisci, you have a loss of fluid from the loaded area, you have large deformations of the cartilage, and the stresses are progressively transferred to the solid phase of the cartilage, so the collagens, for example. And if they get damaged, they don't repair themselves. So there is a higher chance of collagen and proteoglycan matrix damage. If you have a gruent contact, like the hip joint, there is almost no loss of fluid. There is very little deformation of the cartilage. And 80% of the total stress is carried by the fluid. Basically, you walk on water. Okay? And this is very important to protect tear and wear of the joint. Okay? Thank you very much. Yep. See you. Is it me? Oh, okay. Let's see whether I have with sound. So I indicate sometimes I have no sound, so you can.
Knee presents some unusual challenges. First of all, the rough surfaces can abrade the new meniscus implant. However, patients with rough surfaces are just the ones who benefit from having a new lateral meniscus. The steps involved are first examination and cleanup of the joint. Next,
If it's not too loud, then yeah. Good morning. Okay, the next presentation is about meniscus biomechanics. So the meniscus is between the femur and the tibia, and we have two menisci. Okay, so one on the medial side and one on the lateral side. Okay, and they make sure that they act as cushion to absorb the shocks of dynamic loading, and also they stabilize the knee and they lubricate the knee. Similarly to the cartilage, meniscus also contains fluids, and that's also how they lubricate the knee. Okay, so together with the ligaments, the ACL, the anterior cruciate ligament, the PCL, posterior cruciate ligament, the MCL, the medial collateral ligament, the LCL, the lateral collateral ligament, the meniscus on the medial and lateral side, they all stabilize the knee. Okay? What people often forget is that these are passive stabilizers, but during walking, you have your muscles, which are very important as active stabilizers. And altogether, they stabilize the knee. Okay, so meniscus consists mainly of type 1 collagen. So there are different types of collagen, and cartilage consists of type 2 collagen, but the meniscus consists mainly of type 1 collagen. There are again some proteoglycans, like in the cartilage, and some elastin. Okay. So this is a top view on the tibia. Okay, so you can see here the lateral meniscus, and here the medial meniscus. You can see that they kind of are adapted to the shape of the condyle of the femur, so that they can make a nice conformity with the condyles. So this is the lateral side and the medial side. You can see also that the shapes are slightly different. The shape of the lateral meniscus is more circular, and on the medial side, it is a little bit more elongated. You see that? So that's how you can recognize a medial and lateral meniscus. The medial meniscus on the front, on the anterior side, is thinner, and on the back side, it's wider. That's also how you can tell whether it's the posterior or anterior side of the medial meniscus. And the menisci, they need to adapt to the shape when the knee is flexing, because the condyle curvature will change. So the menisci are flexible, and they are attached at certain spots. So the medial meniscus is attached on the anterior and posterior side at the horns. So this is the meniscal horn. This is another meniscal horn. And these sites of fixation we call meniscus horn fixations. And on the medial side, so it's the capsule, the meniscus has grown into the capsule. So there is some fibrous tissue connection, okay? On the lateral side, the meniscus is more mobile, okay? So it's connected only here at the horns. There's no fixation to the capsule. And it also means a little bit that typically the lateral condyle of the femur moves more than the medial one. So the medial one is more stable. It rotates, the knee rotates a little bit on the medial side, and the lateral side is moving more, and that is accommodated by the meniscus that can move more, that is more mobile, okay? Okay? Okay, so the function, one of the most important functions is the load absorption and load transfer and smoothing of the load, which you can compare like with this truck. It is supported by these devices to make sure that the load is equally transferred. So this is, let's say, an equal load transfer. You can see here, let's say, the stress pattern. And if that is gone, we call that a meniscectomy. If you remove the meniscus, then the load is transferred on the middle part only. So the condyle of the femur will load directly on the cartilage of the tibia. And then you have a hotspot here. And then, as we saw earlier, the collagen will be damaged on the longer term, and people will get osteoarthritis. So let's say 30 years ago, if you had a problem with the meniscus, the surgeon would not have any doubts to remove the meniscus. After 30 years or 20 years, we know now that that will lead, in a high number of cases, to osteoarthritis. So the surgeons will not remove it easily, but will try to treat it. Okay? So if I make a cross-section of the joint, so I make a coronal cross-section like this, I look here against the condyle of the femur, I look here at the tibia, and I have a cross-section now of the meniscus, okay? What we see here is that this is then the capsule. So this is the medial meniscus, and there is interaction by blood vessels from the capsule to the meniscus. And it's only until this part that there are vessels, blood vessels, vascularization. So we call this the red zone. I can show it here, the red zone. This is schematic drawing. So here we have the capsule. This is the femur, the tibia. This is the meniscus. We have the red zone, which is vascularized. We have the red-white zone, which is less vascularized. And we have the white zone. The white zone is because the meniscus is white. It is not red because of vascularization. So it means that if there is a problem here, the meniscus is able to heal itself. If there is a problem here, which often occurs, the meniscus is not able to repair itself. The body is not able to repair itself. So it depends a little bit where a lesion occurs, whether the meniscus is repaired by the body or not. Okay? So we call it the red zone and the white zone. Okay, there are two types of meniscus problems, and that's because of traumatic injury, so like football players or soccer players. I'm not sure about cricket players, but I guess so. Or it's just degeneration, because in time the meniscus also loses its property, just like bone and just like other tissues in the body. Okay? Now, the injury of a meniscus can have many different aspects, and surgeons have tried to categorize that, because then for each category, they can define how a surgery or how the treatment should be. So you can have a flap tear, which is very at the border. You can have a torn tear, which is basically at the horn. Yeah? So there's a piece sticking out. A bucket handle tear, which means a fissure in the meniscus. And this is quite common, a bucket handle tear. Or you can have a transverse tear, which is a kind of a crack almost, or a tear from outside to the inner side. You can see that most of the cases, it is in the white zone. In the red zone, there are hardly any problems, or maybe if there are problems, maybe the body can take care of it itself. We don't have to treat that. Here you can see a picture of a with meniscus. So the meniscus should have this shape, but a number of people are born with a round circular meniscus, and often they don't have any problems because everything adapts to that. So the bone gets also a little bit of a different shape. But if they do sports or high activity, other high impact activities, and then the discoid meniscus is torn very easily. Actually, my son has this problem, and it was interesting to see that his condyle had a different shape than commonly. So I found it very interesting. And the surgeon then basically goes in with an arthroscopic surgery and cuts it as a new meniscus, and then the bone has to adapt. And if the patient is young enough, the bone will adapt to a normal shape. So it's very interesting to watch how biology solves a lot of problems. Okay, so a meniscus tear happens quite frequently, and again, some of you might have a meniscus tear without any problem. But yearly, out of 100,000 people, they do 250 surgeries, so it's quite common. And the medial side is the biggest proportion. Okay, so although the lateral side is more mobile and you would expect that there would be more problems, the medial side has bigger problems. And that is also because the load that we have in our body goes more to the medial side than the lateral side. So the meniscus on the medial side is loaded more heavily. And I guess that is also one of the reasons that we have more medial problems. Okay, so if you have a meniscus tear, it can result in pain, not of the meniscus itself, because there are no nerves in it, but because of the subchondral bone, and it can basically lock your knee, or you feel sensation of locking, and it can result, of course, in overloading of the cartilage, and it needs to be repaired. And this is, for example, a common tear, the bucket handle. You can see it here nicely. So the rim is still okay, but it's a fissure inside the meniscus. Okay, so here you can see the red zone. So it's vascularized. And if the lesion is in this zone, it has a bad intrinsic healing capacity. Okay? So how do we repair meniscus lesions? Well, we can do a meniscectomy. So we remove the meniscus, or you partly remove the meniscus. We can try to repair it with sutures or staples. We can have an allograft implantation, which basically means that you transplant a meniscus. I will show that later. Okay, so from a donor, there is a transplantation of a meniscus. Or you can generate meniscus substitutes. So like a collagen meniscus, that's kind of a tissue engineering approach, or a scaffold that people work on. It's also kind of a tissue engineering approach. So within the lesion, you put in new material so that it's healing. Or you can develop a permanent replacement, like we do with a total hip and a total knee replacement. You can also have a total meniscus replacement. I will show that. So we start with a meniscectomy. Okay, so with a meniscectomy, the surgeon will cut away the loose part. And this is then called a partial meniscectomy. And virtually all meniscectomies are partial, because what they always try to do is they want to retain the rim of the meniscus to have still some stability. Okay, so it's very rare that a full meniscus is removed. But sometimes they remove a big part of the meniscus. So you can have a partial meniscectomy. It's an arthroscopic procedure. Okay, so it's minimal invasive. It's the loose bits are removed by just trimming, like we saw earlier. And some people say that there is some evidence for partial meniscus regeneration. But the tissue that is formed is certainly not the meniscus type of quality that we would need. You can have a complete meniscectomy, which people are more often do now arthroscopically, but still some surgeons use an open surgery for that. You remove the complete meniscus, that is either medial or lateral, completely to the rim, to the capsule. So you remove it completely. And this, of course, could lead to osteoarthritis. This is quite an old concept, and people do that less and less because we know it will result in osteoarthritis. But sometimes there is no other option, and the surgeon just have to treat the pain. Okay, I'm going to show you how a meniscus is repaired and a meniscectomy in this video.
Meniscus tears are sometimes repairable. The outer rim of the meniscus has a better blood supply. This is known as the red zone. The inner part of the meniscus has very little blood supply. It is known as the white zone. The red-white zone is in between. The farther into the red zone the tear is, the more likely it can be repaired. Meniscus repairs are often done arthroscopically, meaning that they are done using a scope rather than by making a larger incision. Once the sterile water is flowing into the knee and the tear is well visualized with the camera, special instruments are used to pass suturing thread into the joint. The special instruments are then used to sew up the torn part of the meniscus. It is best to repair the meniscus if it is repairable to keep as much shock absorber as possible in the joint. When the meniscus is repaired, the repair must be protected by not walking on the knee until it has had time to heal. This means a few weeks on crutches. A person who has a meniscus repair should work on gentle range of motion to prevent the knee from becoming stiff. If the blood supply to the torn part of the meniscus is poor, attempting to repair the tear is useless. This is because the nutrients needed for healing cannot reach the tear. While stitches might hold the torn edges in place, the edges will never heal back together. Only the outer edge of the meniscus has enough blood supply for a successful repair. When a meniscus tear is not repairable, the torn portion of the meniscus is shaved away. This results in a smoother edge that does not catch or cause pain. While it is good to leave as much healthy meniscus as possible, it is better to remove the torn portion as it can continue to catch, cause pain, and wear away at the articular cartilage. This procedure is known as a partial meniscectomy.
Okay. So it's illustrated how difficult it is to get a long-term fixation if you repair it, if it's not in the red zone. Okay, so meniscal repair, as you saw, is done with sutures or sometimes with staples, and all kinds of companies and researchers are trying to establish the best mechanism, because if it's not healing, it means that the staples or the sutures need to function for the rest of your life. And it's very challenging, of course. So, because if we do a fracture healing of bone, we need only a temporary functioning of that fracture fixation device. So it's okay. If we do hip replacements, it needs to function for the rest of your life. So that's very challenging. The same goes for these staples. If it's not leading to a repair of the meniscus itself, then this needs to function for the rest of your life. So that's challenging. So you can have all kinds of staples and sutures that are tested, and people test it in terms of let's say strength, because it needs to be very strong, and you can imagine that depending on the design it can be stronger, but usually if it's very strong, it could also mean that it's surgically very challenging to get it done. So we are looking, of course, for a very easy surgical solution, which is lasting for a lifetime, and that's not so easy. So, for example, if you have some anchors, so this is one of the anchors, you have quite high failure rates, and there is a lot of literature about that. So that is maybe not an optimal solution for all patients. Another solution could be an allograft implantation, and that is also very challenging. So it means a transplant from a donor. And it doesn't happen very frequently yet, but I'm working with meniscus, with surgeons who do meniscus replacement, and in their minds, it could be a very good solution. So the indications are for patients that have had a meniscectomy, okay, and that they still have pain and discomfort, and that could be associated with osteoarthritis. So they are at the beginning stage of osteoarthritis. And patients undergoing ACL reconstruction for increased stability. So they often have a mutual injury. As I told yesterday, ACL injury is often associated, or you damage your knee, not only one ACL, but you injure a lot of tissues. So ACL is often accompanied with meniscus damage. And it's applied, especially now, because it's quite experimental yet, for people who are very highly active. The donor menisci can be freshly taken, or they can be freeze-dried. Okay? So this is then how it looks like. So you have a meniscus of a donor, but of course, the fixation is extremely important. And as far as I know, they only do now the lateral part. So this is the medial meniscus, we can recognize it now. This is the lateral meniscus, and the fixation is problematic. So what they do is, from the donor, they include already the fixation. So this is a bone piece, okay? And the bone piece is a rectangular piece of bone, which they remount here for the patient, and they, like a puzzle, it's laid in the generated cavity by the surgeon, okay, and then it's fixated because bone will heal, but if you would cut it here at the horns, it will not heal itself. And if you would staple it or suture it, you would challenge the duration of the staples or the sutures. So bone healing is more reliable than using artificial solutions or synthetic solutions. So this is how it looks like, okay. And I'm showing now a video which is 7 minutes, so that's quite long, but I think it's amazing how they do that. And this is from the Stone Clinic, and Dr. Stone is one of the pioneers in this field of meniscus replacement.
Lateral meniscus replacement in the arthritic knee presents some unusual challenges. First of all, the rough surfaces can abrade the new meniscus implant. However, patients with rough surfaces are just the ones who benefit from having a new lateral meniscus. The steps involved are first examination and cleanup of the joint. Next, the torn remnant of the lateral meniscus is debrided back to a stable base, taking care to preserve as much of the rim as possible in order to prevent lateral meniscus subluxation. After trimming the inner portions of the remnant lateral meniscus, a needle brought through a guide is used to bloody the meniscal rim and bring in a new blood supply. The needle is used in a Singer sewing machine type motion in order to create bleeding into the lateral meniscus rim. Next, the trough for the bone block of the lateral meniscus is identified and marked from anterior to posterior along the pathway of the ACL. After marking the path, a 5mm burr is used in order to create the trough. Care is taken to pass the burr from anterior to posterior and not penetrate through the posterior capsule. It's very important that the depth of this trough exceed the height of the bone block on the meniscus, so that the bone block sits into the trough in a stable fashion. We check with a curette to make sure that the trough extends all the way posteriorly so that the bone block is not artificially positioned too anterior in the joint. A customized meniscus transplantation guide that has a spoon on its tip to capture the guide pin is passed into the anterior lateral portal and into the trough just created. A guide pin is passed up to the tip of the spoon and then over-drilled with a 4.5 millimeter cannulated drill. A curette is used to capture the tip of the guide pin and drill so that it does not pass into the posterior structures. A suture passer is passed up the guide pin and the suture exits the anterior lateral portal. And the step is again repeated at the anterior aspect of the trough. And then again at the posterior 1/4 of the tibial plateau, just posterior to the popliteus. Each of these sutures are brought out the anterior lateral portal, which is slightly widened in order to prevent tissue capture of the sutures. Attention is then turned to the cadaveric lateral meniscus, which comes either on a half bone block or a full block. The peripheral attachments are divided, taking care to preserve the synovial and ligamentous attachments on the side of the meniscus cartilage itself. The width of the bone block is then identified and marked with an oscillating saw, usually about 5 millimeters in width. The bone block is then cut free from the tibial plateau and then sized to fit in the trough created. A suture loop of permanent suture is then passed around the bone block anteriorly, posteriorly, and at the posterior 1/4. Walgenbach lines are marked on the bottom of the meniscus in order to help determine the top and the bottom when inserting the meniscus itself. The previous placed suture loops through the 3 tunnels are then looped around the sutures placed on the meniscus allograft. The anterior lateral portal is slightly widened in order to permit passage of the bone block in one step. The meniscus transplant is then pushed through the relatively small hole at the anterior lateral aspect of the knee that permits meniscus transplantation. Once pushed into the knee, the bone block is pushed down into the trough. By using an arthroscopic obturator, the knee can then be extended, further embedding the bone block into the trough. The sutures are then secured on the external aspect of the tibia. An inside-out meniscus suturing technique is then used, with the sutures exiting the posterior lateral aspect of the knee through small percutaneous punctures. We no longer make open posterior medial or posterior lateral incisions, as we've found the risk of nerve entrapment is reduced when we use small percutaneous sticks. Care is clearly taken to exit these sutures anterior to the fibula and to protect the perineal nerve. Once the sutures are tied, the sutures have been passed on the inferior and superior surface of the lateral meniscus transplant. Next, a Kasperi suture punch is used to fix the anterior 1/4 of the meniscus to the anterior capsule. A final check of the meniscus position within the knee is made to ensure that the meniscus is secured throughout, and then the patient is returned to the postoperative recovery room. It should be noted that if treatment of the articular cartilage is performed at the same time for the arthritic knee, the paste grafting of the articular cartilage is then performed after the meniscus transplant has been placed. Marking is instilled in the knee, closure undertaken, and the patient returned to the post-op recovery room. The postoperative program for lateral meniscus transplantation focuses on a straight leg brace for 4 weeks with touchdown to partial weight bearing, since the lateral meniscus transplant is stable in full extension. Daily exercises and out of brace range of motion is carried out multiple times a day from 0 to 90 degrees. Trunk stabilization exercises, upper body workouts, well leg bicycle are all initiated on the first day postoperatively. A coordinated rehabilitation and training program is essential for returning the patient to full sports. Sports other than swimming and cycling and weightlifting are generally deferred until after 4 months. Patients are encouraged not to go into flexion past 90 degrees except with physical therapy for the first 3 to 4 months. Patients with lateral meniscus transplants, even in the arthritic knee, have been successful at returning to full sports since the meniscus transplant seems to provide an excellent shock absorber for the joint.
Okay, well, I thought it was quite an impressive piece of surgery, that you can, through such a small hole, you can maneuver that meniscus. It completely folds, and then it's unfolded in that very small joint space, and it matches exactly. So yeah, I found that quite impressive. You can also see that this is done for sports athletes in the Stone Clinic. So many sports athletes who have problems go to Dr. Stone, and it's still, let's say, it's a challenging surgery, and not every surgeon can do that. You can imagine that. Okay, and you saw that they use 3 sutures to fix the bone. But the sutures is probably of degradable material, and the bone then will make sure, because of the healing, that the fixation of the lateral meniscus will take place. And you also saw that before 3 or 4 months, the athletes are not allowed to flex more than 90 degrees, and that is because the lateral meniscus will have to move to accommodate that. So in order not to challenge that, they are not allowed to do that. Okay, so of course the meniscus, the allograft has to have the right size, so they select the donor meniscus size with the size they need, and that is also not so trivial. So it has to have a proper size, because if it's too large, like in this case, it's not able to fulfill its function. So this is, if you have an intact medial meniscus, people have done, let's say, TEC scan stress analysis measurements, experimental measurements. So this is with the intact medial meniscus. So, and this is after a meniscectomy, and this is after a meniscus replacement with an allograft. Okay, so the stresses are, let's say, almost normalized. Okay, so if you use a meniscus allograft, what are the contrasts? It's availability, so there are not many donor menisci available. It's of course not reproducible, the material comes from donors. There is a lack of control of the mechanical properties and its composition, and there is a potential for disease transmission, although that chance is not so big. But if you use donor material, there is always a chance. The survivorship is still unknown, and the surgical technique is very challenging. Okay. On the positive side, it allows for a complete replacement, and the sutures, as you saw, will not function for a lifetime, or at least it's very difficult to get that. And meniscus allograft is effective in the intermediate term for decreasing pain, and we will have to see how it goes on the longer term. Because on the longer term, we need clinical studies to see whether it's really effective or not. Okay, so meniscus substitutes. And we first look at the collagen meniscus implant. This is also commercially available. And it's being made of Achilles tendon, bovine Achilles tendon. So they process that into this meniscus. So they trim it, they purify it, filter it, and they mold and cross-link it so that they can get this collagen meniscus implant. So it's made of collagen. And the idea is that eventually it will be resorbed, and the meniscus, or partly resorbed, and the meniscus tissue will be formed. So this is also not a complete replacement, but because you need a vascularization. It's only a partial replacement. You need to have an intact rim of the meniscus over the entire length to support the meniscus replacement. You should not have unstable segments, and it should have a lesion in the red zone or in the red-white zone, because the transplant is a collagen and it needs to be replaced, so it needs to have vascularization. It needs to have cells to be able to transfer it in healthy meniscus tissue. So this is very challenging. So it's not suitable for a total meniscus replacement, and it's certainly not cannot be used if there is malalignment of the leg. So, for example, if you have a leg and the meniscus is, let's say, damaged, and if that is coincided with a leg axis that is not correct, the meniscus will fail also. So you need to have a healthy leg length and a leg axis, because otherwise the stresses will be too high on the meniscus. Okay? Okay, so the indications for such a collagen meniscus are that it's a mild meniscus problem, okay, and you have to have that intact rim. And it's now only available to treat the medial meniscus, but we saw earlier that 75% of meniscus problems happens on the medial side. Now, this is still also a little bit of experimental, and there are not many CMIs used worldwide, so it's around 2,000, and the clinical studies are now underway. We know that the meniscus implant, when it's implanted, it tends to shrink, and that its initial mechanical properties are poor. So it's quite soft. If you have it in your hand, it's very soft. So the patients have to be also careful at the beginning if they receive this collagen implant. Okay, so you can imagine that. So if I tell you all of this, you can feel that meniscus problems are not solved at all yet. So there is a lot of research going on in this very small piece of structure in our body. So we also do, for example, research on developing a scaffold that we can implement into a torn meniscus. So it would look like this. It's like the collagen meniscus, but the idea is also that it partially replaces the meniscus. It cannot replace the full meniscus. And we can use different materials. So these are all porous materials. These are synthetic materials. The collagen meniscus is made of from a donor or a bovine origin. This is synthetic material. You can use estane or polycarpolactone, polyurethane. And the idea is also that they resorb in time. And you can imagine you can play around with all kinds of material properties, the porosity, the stiffness, the resorption, the degradation grade. And of course, we would like to have a high modulus at the beginning, but also a high porosity, and that is a contradiction. So if we make it very porous, the modulus, if we make it very porous, the modulus goes down. So these materials typically are too soft for real functioning. So we rely on cells and on meniscus tissue formation. In time, they degrade, and of course, we do not want them to degrade too quickly. Because if they degrade very quickly, the body doesn't have a chance to replace the meniscus. So that's also an issue. So this is a study that we did in animals. So we are going to look at the ingrowth of tissue into the scaffold, the differentiation into fibrocartilage, because that's what we want to achieve, the changes of the mechanical properties in time, and we look at articular cartilage degeneration. So because that's the whole goal. We want to stop cartilage degeneration. Okay, so this is how we fixed it at the horns and at the capsule. And we used a dog model. So we have, these are beagle dogs. We replaced the lateral meniscus. And the dogs were mobile because it's very difficult to have a dog not being mobile. That's of course a challenge. And when we harvested the menisci, and we can look at the menisci from a histological point of view, we see collagen type 1, which we would like to achieve, because the meniscus is primarily consisting of collagen 1. We can see at the rim where the red zone is, that there is a lot of formation of collagen 1, and there is even some collagen 2, more at the central part. So that is that's let's say a good sign that we have this tissue formation. When we look at the mechanical properties, we took a punch out of the meniscus, yeah, and then actually loaded and determined the mechanical properties. So if we start with the meniscus before implantation, it looks like this. So it's very soft. Okay, so you don't need a lot of stress to deform it a lot. Okay, it should say deformation instead of compression. So the deformation is a lot. But after some months, so after 6 months, we see that the tissue starts to like an intact, the native meniscus. You see that? So this is quite successful, and in fact, this material is now on the market for partial meniscus replacement. When we looked, however, at the whether we could prevent cartilage damage, it turned out that that was not the case. So this is a meniscectomy, which would have a large amount of meniscus damage, right? So this is the Mencken score, and the Mencken score, if it's 0, there is no damage. If it's 14, there is a lot of damage. Now, we scored, let's say, 5 for a meniscectomy and for the prosthesis. So, and basically, you see that there is no difference, not after 3 or not after 6 months. So we are, in terms of cartilage damage, as bad as a meniscectomy. So the implant does not prevent cartilage damage. So that we were able to generate some meniscus tissue, but not prevent cartilage damage. And some surgeons say, well, that's not so problematic. As long as I prevent and I can remove the pain of the patient, that is my primarily goal. And what happens to the cartilage, we will see later. This is a temporary solution. And if I have to put in an implant, a prosthesis, a total knee replacement after maybe 15 years, we have bridged that gap of 15 years. Okay, so we saw that a new meniscus is formed, collagen type 1 on the outside, fibrocartilage on the, in the center. We couldn't prevent cartilage damage, but it's probably used for repairing a partial meniscectomy, and that's now marketed by a company. Okay, what you can also do is develop a permanent meniscus. So the permanent meniscus is not supposed to be resorbed. And so we worked on that, and our idea was to replace so this is the medial meniscus. Huh? So what we want is to replace the medial meniscus and compare that to an allograft. Okay, so we want to be at least as good as an allograft, because there is a shortage of allografts, and the allografts are currently used for young patients and active patients, as I saw, it's more for sports athletes, but there is no solution yet for older patients. So this is our meniscus replacement. It's basically made of kind of a rubber. It's polycarbonate urethane. It's called Bionate. Yeah, and it's quite flexible, and it is supposed to stay there for a lifetime. So we did a lot of research, and these are the questions that we addressed, and I will go over them subsequently. Okay. So the first question is the geometry variation in shape of the meniscus due to size or shape? When you develop an implant, it needs to fit in the knee. Okay. So like a total knee replacement, like this total knee replacement, it comes in different sizes. Okay. And then you wonder, should the size be just enlargement, or should it also change shape? And I can imagine for the meniscus, because it needs to be conforming with the femoral condyle so well, it may also be due to shape and not only due to size. Right? So you need to change maybe the geometry. So are geometry variations due to size or shape? So we did an MRI study, and we looked at 35 healthy individuals, and we segmented from the scans the menisci. So you can see the shape here. Okay, so these have all different sizes and shapes, and you can do a principal component analysis on that. So basically you stack them all together, and you say, okay, is it only enlargement or is there also shape change? Okay, so this is then the result. So you can see here all kinds of points on the surface of the meniscus, and you can see here the size difference. That's principal component. It's one principal component. But you can also see that there is also some shape change amongst these 35 menisci that we segmented. Okay, so that gave us an input about whether we should only focus on size or also on shape. It turns out that the size of the meniscus is most important. So 54 of the change in geometry is due to size. So it's just different sizes. But the shape is also important. So when we generate these implants, we need to think of having also different shapes, and that the surgeon can assess what shape he needs before the surgery. Okay, so most of the geometry variation is due to size variation. So how does geometry variation affect the stress level in the cartilage? Because we need to determine how many sizes of the implants we need. And if we can have only one size, it is cheaper to make than if you need very small steps in size, because if it's very sensitive to the stresses on the cartilage, then we need to have multiple sizes. So we assess that with a finite element model. I think that is very suited for this question. So we have a finite element model, we have the cartilage, we have the menisci, okay, we have the cruciate ligaments, and we can assess, we can change now the shape and the size of the meniscus, and then we're going to calculate what it does to the cartilage stresses. Okay, so we calculate the stress patterns on the medial cartilage, on the tibia. So you can see here the tibia stress, and you can see if we make it larger, if we make the meniscus larger, we can see that it looks like a meniscectomy, and that's logical, because if you have here a condyle, and if the meniscus is too large, the condyle will rest completely on the tibia, right? If you make it smaller, it rests on the meniscus. So you can see if you make it smaller, the stresses are absorbed by the meniscus, okay? However, so if we make it smaller, the deformation of the implant becomes larger because all the stress goes through the meniscus implant, okay? And that could lead eventually to damage of that implant. It could result in failure of the implant. So eventually, so this is a well-fitting meniscus, which is a kind of a compromise between the load that is transferred on the cartilage of the tibia and the deformation of the meniscus implant. Okay. So if the prosthesis is too large, it loses its function. Yeah? It doesn't transfer the load. If it's too small, it is loaded too much and will fail. Okay. So how is the meniscus functioning relative to an intact allograft or meniscectomy in a cadaver study? Yeah. So we checked its functioning. And so we have a cadaver loading frame, and we implanted in the cadaver a meniscus prosthesis. The intact meniscus, we left it intact first, an allograft or a meniscectomy. And we looked at the stress levels again. And we can measure the stress levels, and we use TechScan sensors for that. And TechScan is a pressure-sensitive film. Okay, so if you push on it, you get a readout. And if you push on it on a larger area, you get a readout of a bigger area with lower stress, okay, a lower peak stress. So this is the natural meniscus. You can see that the pressure on the cartilage is globally distributed. The prosthesis and the allograft have some higher peaks. You see that? Huh? So the collagen will be more damaged. And if you do a meniscectomy, you see a concentration. So our conclusion was that our prosthesis was as good as an allograft, maybe a little bit better in this case, okay? But certainly not as good as a natural meniscus. And that is typically for all the procedures that we do, it is not possible to replace the natural meniscus yet and have a functioning of the natural meniscus, resembling. So the prosthesis behaves as good as an allograft and perhaps better than a meniscectomy, as we see here. So can the implant endure longer term in vivo loading? And we did that with an animal study, okay? So we had goats for this purpose. And you can imagine we needed to make new menisci implants because the human meniscus implant is too big for a goat. It didn't fit. So we make a goat-specific implant, and we evaluated the histology of the meniscus and the cartilage after 3 and 12 months. So this is a long time for an animal experiment. So the goats were walking around with the meniscus implant for 12 months. So first of all, we looked at the deformation of the meniscus, because what we see with an allograft, if you have an allograft, so in this example, so this is then the lateral side, because we see here the fibula. If you load the femur, an allograft tends to protrude outside. So there is expansion of the meniscus, and you can see the meniscus going outside of the condyle. So because it's pressed by the condyle outside of the knee joint, let's say. And you can see that it's called extrusion. So typically you can see that the meniscus is then going out of, from the condyle area. So it's extrusion. So we can see here the extrusion of the implants, of the allograft, of the control, that's an intact meniscus, and of a sham operation, which is just a surgical intervention without doing anything to the meniscus. So you can see that we have some extrusion of the meniscus in the order of 1 millimeter more than the intact meniscus. Okay, so there is a little bit of loss of function due to daily loading in that goat. But it's very similar to what we see in the allografts. And from the allograft, we know it functions quite okay. All right? So prosthetic deformation is limited to 1 millimeter and is similar to what we found with an allograft. Okay, so what is then the influence of the implant on the cartilage in that goat model? So we do histology. So we do histology with the prosthesis, the natural meniscus, the allograft, and the meniscectomy. And you can see here, for example, that in a meniscectomy case, we see damage of the surface, which you do not see in the prosthesis. In the allograft, we see some damage. In the natural meniscus, there is no damage. In conclusion, and these are only a few pictures, and the conclusion was that the prosthesis behaves as good as an allograft. Okay? But it was not as good as the natural meniscus. So in conclusion of this study with this permanent meniscus, a meniscus prosthesis has been developed which shows the same functioning as an allograft. And future work will focus on the fixation before it can be implanted, because what we didn't look yet at the fixation at the horns, and that is very challenging still. But we are in the process of developing that. And when we look at overall what I presented today, we can say that nothing has been developed which is as good as the natural meniscus. Okay, thank you very much.
I think there was this question that when we do joint replacement, where does the synovial fluid go?
Okay. I think we do that question after. Good afternoon. The next presentation is about knee pathology, and it's an intro to total knee replacement. Okay. So first I start with a movie that shows what we can do with people who have osteoarthritis. Oh.
Osteoarthritis, also known as degenerative joint disease, is one of the most common causes of knee pain. More than 85% of people over the age of 65 have knee osteoarthritis. Some people suffer from knee arthritis at a much younger age. The knee joint is comprised of three bones: the thigh bone, the femur, the shin bone, the tibia, and the kneecap, the patella. The ends of the bones are protected by a rubbery cushion called cartilage. Cartilage does a wonderful job of absorbing the impact of walking, running, and jumping. Unfortunately, it has a very poor blood supply and does not heal itself very well when it is damaged. Over time, the cartilage can wear away like treads on a tire. Why some people suffer from arthritis at a much younger age than others can be a difficult question to answer. Anything that places more repetitive stress on the cartilage can make it wear away more quickly. Obesity can place a lot of stress on the knee. So can jobs and lifestyles that require a great deal of walking or climbing. A traumatic injury to the knee can accelerate degeneration of the cartilage. Genetics probably plays a role as well. As the cartilage wears away, the bone underneath begins to be damaged. This causes pain, especially with bearing weight, climbing stairs, or getting up from a sitting position. Doctors can often recognize arthritis on an X-ray. The space between the bones that is normally occupied by cartilage becomes more narrow as the cartilage wears away. As the bone underneath is damaged, cysts and bone spurs may form. Without the smooth surface of healthy cartilage, the knee may begin to grate and grind. The knee becomes stiff. As the knee becomes irritated, it swells. Sometimes the swelling is excessive, filling the knee with fluid. This is a condition known as a knee effusion. The effusion can add to normal arthritic pain by building up pressure inside the knee. This can be very painful and may make it difficult to bend the knee. If a large effusion is present, the fluid can be tapped. This is a procedure known as a knee aspiration. People who have a large effusion aspirated often feel instant relief. Treatment for osteoarthritis depends on the severity. Early arthritis can be successfully treated with anti-inflammatory medications such as ibuprofen and naproxen and appropriate exercise. Injecting a steroid into the knee can be very effective in relieving pain. Many people refer to this as a cortisone injection. A series of hyaluronic acid injections can lubricate the knee like motor oil and provide relief. These injections are made by several different companies and have different brand names. As knee osteoarthritis worsens, anti-inflammatories, physical therapy, and injections become ineffective. Surgical options may be considered. Knee arthroscopy, or a knee scope, may provide temporary relief by cleaning the knee up from the inside. A camera is inserted through a small incision. An instrument, such as a shaver, is inserted through another small incision. Damaged cartilage can be debrided and loose cartilage can be removed. Knee replacement surgery may be necessary in cases of severe arthritis. An incision is made lengthwise down the front of the knee. The patella is pulled out of the way to expose the knee joint. The arthritic surfaces of the bone are removed. Metal implants are then cemented to the bone. A plastic spacer is placed between them. The knee is then closed and dressed. Following knee replacement surgery, physical therapy is helpful in order to return the knee to its full range of motion. Many surgeons allow their patients to walk on the new knee the day after surgery. Knee replacement surgery is proven to be effective and relatively safe.
Okay, so this is kind of a global overview about the choices that a surgeon has. And I will go over in this presentation about, I will deepen these choices. So osteoarthritis. Typically it occurs in patients who are older than 50 years. And of course there are differences, but this is typically. It can also be secondary, that you call that secondary osteoarthritis, which is due after a trauma, for example. So there is something changed in your knee, like a meniscectomy, and then you get osteoarthritis due to something that has been not normal. And that's happening often in younger patients. But the bulk of the people have it due to degenerative diseases, let's say. So the symptoms of osteoarthritis are gradually increased complaint. So it's chronicle. It's increasing, and then there is a level that you go to a doctor. And it's pain. It is accompanied with morning stiffness and starting pain. So if you come out of bed, you need to really start up, and that involves also pain. And this becomes longer and longer, this period, until you can't take it anymore. People cannot walk anymore for a long distance. They're less mobile. And like the video showed, it goes along with swelling of the knee. And you could also have knee locking complaints. Okay. On an X-ray, the first thing a surgeon will do if you come with these complaints, they will make an X-ray. And they can see often that the joint line is diminishing. So here you can see this is the femur and the tibia. This is the lateral side because I see the fibia. And you can see here the joint space. This is rather healthy. I will show in the next slide a really osteoarthritic case. So we can have subchondral sclerosis. So that is that this bone here densifies because of a reaction of the high loads. And you could have osteophytes, which are the spurs on the video. So the bone responds due to the unnatural situation by adding bones at locations that you should not have. Okay, so this is optimally the surgeon makes a full leg X-ray. So you can see here the alignment of the leg, and basically you should have a straight line from the center of the head. You can see that this patient also has a hip replacement. Huh? You see that? A straight line to the ankle. So you can see already that this is bended inwards. Okay, so this is a valgus knee. If it would be bended outwards, it would have an O shape. It would be a varus knee. This is a valgus knee. And you can see here on the lateral side, there is no joint space anymore. So the cartilage has disappeared. So we need to do something about it. So the surgeon will look at the varus valgus angle and to this X-ray. And he understands now where the pain comes from. So you can treat this conservatively or with an operation, as we saw in the video. And it depends on the cause, on the amount of pain, on the age of the patient, the stage of degeneration. And recently we would add now the expectations of the patient. Because if the expectation of the patient is that they want to just stay at home, maybe an operation is not needed. If the expectation is that they would like to function and work and they're still young, then that expectation is higher and we need to do something else. So expectation management of patient is really very important nowadays. Okay, so here you can see again an osteoarthritic knee with very narrow joint space. Okay, so a conservative treatment could indicate that the person has to adapt the lifestyle, or have to have physiotherapy, or have to lose weight. That's also what is very common. Often knee patients are obese, and the first thing the surgeon will tell to the patient is to lose weight. And that's also because maybe they will treat it with a total knee replacement, but the knee replacement also is can fail if it's subjected to very high load. So to lose weight is very important. Surgeon could indicate to use walking aids, pain medication, corticosteroid or hyaluronic acid injections, as we saw on the video. And these are very helpful to relieve the pain. Hyaluronic acid is also, it's more a lubrication to lubricate the joint. And there is a lot of debate on how effective this is and how long it will be effective. But for some patients, it's enough. Okay, so only if the conservative treatment does not work, we are going to do a surgical treatment. And we can do that with an arthroscopic nettoyage. I will show that. A cartilage repair operation, that's already what we discussed. An osteotomy, and uni knee prosthesis, a total knee prosthesis, or an arthrodesis. Okay, and I'm going to go over all of these. So an arthroscopy of the knee is done, and we showed that in videos before. It's a relatively small surgery, and it's just readjusting the cartilage. It's removing the loose parts, and it's usually, unfortunately, for most patients, effective only for a short period of time. It's usually not a lifetime solution, because if you remove the cartilage, we have seen it on the video, you remove cartilage and that cannot be right. So these are then, this is for example a result of a nettoyage. And that nettoyage is just an arthroscopic surgery. And you can see that this is the cartilage, this is removed. You can imagine that on the longer term this causes problems and pain. And the video also told you that the pain is not felt in the cartilage, but it's in the bone. So if the bone is stressed unnaturally, it's causing pain. Okay, so we can do the repair with the mosaic. We discussed it already. And what is very common in Europe, I'm not sure how common it is in India, but that's a corrective osteotomy. And it means that if the leg length axis is malaligned, like this or like this, we do an adjustment in the bone and not in the joint, because there is something, the orientation of the bone is not correct. Okay, so the axis is, in this case, this is a varus knee instead of a straight knee. And we can solve that by removing a wedge in the bone. Removing a wedge in the bone, it's called an osteotomy. So you make a cut, you make another cut, and that's an osteotomy. So here you can see that. Okay, so this is called an open wedge osteotomy. So the surgeon, this is the medial side. We see here the fibula, that's the lateral side. From the medial side, he will cut, not completely, but until he can hinge the bone. Okay, so that's very delicate. If he cuts too far, he is cutting the bone. If he's not cutting far enough, he cannot open the wedge. So you have to have some training for that. And surgeons use intraoperative fluoroscope to assess how deep they are, for example. Okay, so suppose he has cut this, and then he can open up the bone and put in a wedge. And this can be a bone graft from a donor, It can also be a calcium phosphate material, and that's wedge shape. And typically, if this is 1 centimeter, the correction is about 10 degrees. And this corrective osteotomy is limited to something like 15 degrees or so. Okay, so the wedge is in, and he needs to fix it, the surgeon, and he does that with fixation plates. So this is a plate with screws, and here you can see it. So this is the open wedge osteotomy. Okay, so there is, in this case, this is probably calcium phosphate because it's much lighter than the bone, so it's not normal bone. So I can tell that this is probably calcium phosphate, which resorbs very slowly. He has 2 screws here and 1 or 2 screws on the distal side to stabilize it. Okay, and you can see this is before the surgery, so it's not a straight line, so it's not 180 degrees, and he corrected it with 5 degrees. You can see that, right? So this is a 5-degree correction, and it means that the medial and lateral condyle stress transfer is now changed, because you can imagine in this case the load was primarily on the medial side, right? Because of the mal axis, and that could hurt on the medial side. If he does this correction, more load is going to the lateral side, and the medial side is not loaded as heavily as before, and then the pain is often relieved. The advantage of this is that you do not interfere with the joint at all. It's out of the joint, okay? And surgeons like to do that. If they prefer not to invade the joint. Okay, so you could also do a closed wedge correction, and basically you cut away a wedge of bone itself. So from the patient you cut away a wedge. So instead of adding a wedge on the medial side, you can cut away a wedge on the lateral side, and you can obtain the same correction. The only thing is then, in this case, you have a little bit of leg length shortening. If you add a wedge, it's a little bit of a leg length increase, but it's very minor. It's only 5 millimeters, which is acceptable. Okay? So this is before the surgery, so he has to make 2 cuts in this case, because he has to really physically remove the wedge. And then this is intra-surgery, so the wedge is still open, and then he hinges the bone and closes it and fixates it then with 3 screws on the distal side. Okay, so in that way, the surgeon is able to maneuver the load transfer from the medial side only to the lateral side as well. Okay. Okay, so there can be complications, of course. You can have an infection of the components. It could lead to a non-union if it's not stable enough. So if you have a very active person, or a person, for example, who smokes a lot or with diabetes, fracture healing is compromised then. And if the person is very active, the wedge, everything will not heal. And there will be a lot of force on the plates, and on the screws, and that can fracture also. So that is also, if screws are only used temporarily, because the bone has to heal. Okay, they can compromise a nerve, for example. They can over or under correct. And it depends on the surgical skills. And they can induce maybe arthrosis on the other compartment. Because if there is more load than on the lateral side, perhaps the stresses become so high that that is compromised. Okay. And typically, it's interesting, I don't understand exactly why, but so osteotomies are very often done in Holland and in Europe, and hardly done in the USA. Maybe it has to do something with reimbursement, I don't know, but typically it's more a European surgery, or maybe also in Asia, I don't know, but not so much in the United States. Okay, suppose that we cannot solve the problem with a osteotomy, but we do need to do surgery. And what we could do is we could treat that condyle. So suppose on the medial condyle, that's the most oftenly affected side, on the medial side, we could treat that with a prosthesis only for the medial side. So here you see, and we call that a uni-knee, okay? Because a total knee replacement like this one, this is a total knee replacement, it replaces both condyles, right? But if the surgeon sees that only the medial side is affected, he will use, or he has the option to use, a uni-knee prosthesis because he wants to make the surgery as small as possible, okay? So this is an example of a uni-knee prosthesis. It consists of the femoral part, it consists of a polyethylene intermediate part, and a tibial component which is fixed to the tibia, okay? And these are typically fixated to the femur and to the tibia using bone cement. And bone cement is a kind of a glue, you know? Okay. So this is the technique of a uni-knee prosthesis. So we see on the medial condyle that there is a lot of damage. The surgeon will cut away the space for the tibial implant. It will make the cuts on the femoral component. So you see here the completed bone cuts, and that shape has to match exactly with the shape of the uni prosthesis. Okay, so this shape needs to be cut out of the bone so that it can be placed only in one position. Okay, so here you can see that it's then placed on the tibial side. Okay, so it's fixated on the tibial side. There is also a hole on the femoral side. You can see that it's placed here. And what you do not see here is that there is also bone cement in between. Because often these implants are fixated with bone cement, although there are also implants available with a very rough coating or with something like this, with hydroxyapatite coating, that could be fixated without cement. But I think for unis, usually they use cement. Okay, so this is then how it looks like. Yeah. So this is again on the medial side, because we see here the fibula. This is a medial uni-knee prosthesis. We see here the metal component, and here the femoral component, and we see a space here. There because we cannot see the plastic on an X-ray. Okay. So here you can see the X-ray from the side. And the surgeon will look at this and will estimate whether he has placed it correctly. Okay. So the indication for a uni-knee prosthesis is that the patient has increased complaints despite conservative treatment. So you could do injections and it helps for some months, and then the patient comes back and something needs to be done. And of course, a uni-knee is used if you only have a problem on one side, so on the medial side most often. And the patient has to have a good range of motion, so it has to be a relatively healthy patient, because you cannot do any corrections, you cannot do a malalignment, so the axis, you cannot realign it, because that will jeopardize the fixation of that uni-knee prosthesis. Okay? So the contraindication is that you have osteoarthritis on the medial lateral side. And typically it is not used for patients who are quite old. And that has to do also with the bone quality, for example. So typically they would use then for older patients or a conservative treatment or a total knee replacement. Also with the expectation that for older patients, the total knee replacement will last a lifetime. So if you have a patient of 70 years, the total knee replacement will do fine. If you have serious varus or valgus deformities, you should not use a uni prosthesis because you cannot correct it. And if you do that on the medial side, so if you have a malaligned leg and there is a lot of pressure on the medial side, subsequently you put in this uni knee prosthesis without correcting it, the uni knee prosthesis will be loaded also very high. So the cartilage went away, but the uni knee prosthesis is also loaded to a high extent and will fail relatively quickly. So that's not what a surgeon will choose. Okay, and for example, if patients are obese and if they cannot flex their legs, so basically this means or extend their legs. So some patients cannot extend their legs but have a remaining flexion of 20 degrees because they cannot flex it or extend it further, and then there is something else wrong in the joints. So a uni prosthesis is used for relatively healthy patients with only a problem on one side of the knee. Okay? So there can be, of course, also complications with a uni knee prosthesis. Again, infection. Infection is really a big research area because it's going to be a very big problem in the future, because all these implants last longer and longer, and infection is quite dramatic. You have to remove the implant, and so it's a very good area for research. But you are mostly mechanical engineers, so it's working with infection is difficult. Also for me, but my colleagues are really very interested in doing research on infection. Complication can also be that it's malpositioned. So if the surgeon didn't do it right and it's malpositioned, you can imagine that it's not running, you know, the knee is not running very well. So the stresses are very high. The polyethylene will wear very quickly because it's not aligned very well, and it will loosen very quickly then. And you can have, of course, have as a complication osteoarthritis on the other side. Yeah, and if that happens after maybe 10, 15 years, it's okay, because then the surgeon will opt for putting in a total knee replacement. And then he has covered 15 years for the patient. The advantage of a uni knee prosthesis relative to a total knee prosthesis is that these patients recover quite quickly because the surgery is smaller, it's only on one side. So these patients function almost normally. Sometimes we cannot measure the difference between a patient that has a uni knee prosthesis and a healthy individual. So it's quite successful from a functional point of view. They have a better range of motion, and the cruciate ligaments, the PCL and the ACL, the cruciate ligaments, they are not affected by the surgery. You're just replacing one side of the condyle. And you don't remove as much bone as you do with a total knee replacement. So that's also important for the future if you have to transfer to a total knee replacement. Okay. So if you cannot put a uni knee prosthesis, we go to a total knee prosthesis. Okay. And the knee is a very complex joint, as we saw. We saw menisci, we saw the ligaments, we saw the cartilage behavior. It is very complex. And in addition, there is no knee the same. So we all here have different knees. Okay. Okay, so these knees are all different, and so we have problems with congruency. So if we make a total knee replacement, it needs to fit exactly on that knee, which is difficult. It needs to dynamically act. It needs to move exactly as in the natural knee. It needs to sustain very high loads, maybe sometimes 8 times body weight. And it needs to be stable. So it needs to be stable in the joint. Okay. And in total knee replacement, we always remove the ACL. Okay, so the ACL is always taken away because otherwise we cannot place a total knee replacement. So the ACL is gone. And in some circumstances, they also remove the PCL, and I'm going to talk about that. Okay, so a standard total knee prosthesis consists of a femoral component and the tibial component, the polyethylene insert here, and also a patella component sometimes. So the patella runs here in this groove. You can see here the groove. The patella runs up and down here, the kneecap, huh? And some surgeons will put a kneecap on the patella. I will show that later. Okay, so this is a movie without any sound, so I'm gonna talk a little bit about that, of a total knee replacement. Okay, so the incision is always on the medial side, mostly, because they have to remove the patella. So they remove the patella to have access to the joint. You can see the jig, and the jig needs to be aligned exactly with the long axis of the leg. So they have instrumentation, it doesn't show it, but they have instrumentation to align the jig precisely. Okay, so they make a number of cuts. So this is the anterior cut where the patella is going to articulate, and the posterior cut. This is called the chamfer. That's the oblique cuts, the chamfer cuts. Okay, and then you get this type of preparation. Okay. On the tibial side, they also have a jig, and that jig is aligned to the ankle to make sure that it's perpendicular to the ankle. Okay, and in this case, you see that the patella is also cut, and there's going to be a plastic component from polyethylene on the patella. Okay. A final patella implant. Okay, so the patella plastic component will articulate on this on the groove. Okay. Okay, so I showed you that the patella replacement is done in this video. So they cut away the patella. And again, there is a difference between Europe and America. In Europe, we don't do that most oftenly. So we leave the patella intact, because usually we see that there is some cartilage still on the patella, and it can articulate in this groove, okay? So it goes up and down on the metal. So we have metal cartilage interaction, and it's fine. In America, they do replace the patella with a polyethylene replacement. So it's a very thin polyethylene surface replacement. And the patella is then moving in the groove, and there is interaction between the metal and the polyethylene replacement. So there is a big difference also. And one of the reasons is that sometimes a patient develops anterior knee pain. So they have pain, but they don't know where it comes from. And in the US, it is, the surgeon is there is a protocol that you have to follow. And if a patient has anterior knee pain and the surgeon did not replace the patella by this plastic component, they could be asked to go to law. They could be sued because they didn't follow the exact protocol. Whereas in the literature, we do not find any difference. So that's why the European thought is that you do not have to replace it, and in America they do replace it. They do replace it. Okay. So it's a matter of choice for the surgeon. Okay. So in a total knee replacement, you can also imagine that you can place it in different orientations. So you can do something with the mechanical axis of that knee. You can make sure that the center of the hip is aligned with the center of the knee, with the center of the ankle, by modifying the angulation of placement. The range of motion that is often obtained is about 110, 120 degrees of flexion, and that is enough for us Western patients. But I know that in Asia, the patients require more flexion because they squat a lot or they kneel a lot. So we work with companies to develop knee implants that have a higher range of motion. And these are special then devices. I will talk about that tomorrow. The aim of the total knee replacement is, of course, pain relief. And we can also do some correction of deformities and alignment and restore the range of motion and get a stable knee. Okay? For the standard total knee replacement, as you see it here, the anterior cruciate ligament is always removed. Okay, that's for every total knee replacement, it is removed. The posterior cruciate ligament is retained, we call it. So this is a PCL retaining total knee replacement. A PCL, it keeps the PCL. Okay, the PCL, I will show that stays intact. So what the surgeon will do is also he will inspect the PCL, because if that is deteriorated, he will opt for another type of total knee replacement. Okay, the collateral ligaments need to be intact, because if these ligaments on the sides are very lax, there will be the joint will not be stable, and then there will be a special design of total knee replacement which makes it stable. Okay, but in this condylar design, we need to have very good collateral ligaments. So we need to have good collateral ligaments and a good PCL on the back side. Okay, we have to have normal extension, and the correction, we can do some correction, but it cannot be too large. Okay. Now, this is then a standard total knee replacement. Okay, so this is how it looks like. We see here again the joint space, which is now the plastic. Okay, we can see here the metal. We can see here also some shadow. Yeah, that's bone cement. So it's fixated with bone cement. You can see that. What you also can see here on the lateral view is this. This is the implant with the plastic here. What you can also see is here the patella, and you can clearly see that this is bone. So there is no patella replacement in this case. So they kept the patella as it was. Okay. So a contraindication for the standard total knee prosthesis is that the PCL is not good. It's ruptured, for example. Or you have medial or lateral instability, because maybe the collateral ligaments are not okay. You have a flexion contracture, so the person is not able to extend the leg. There is a varus or valgus deformity bigger than 20 degrees. You have perhaps bad bone quality. If the bone quality is really very bad, you need to, this fixation is not reliable. Okay, so for very osteoporotic cases or in revision cases, we need to do something else. Or if the knee is infected, we need to take it out, and then we need to have a better fixation also. Okay, so suppose that the PCL is not functioning well. So here you see the PCL, so it's attached on the back side, that's why it's called the posterior cruciate ligament. And its function is by flexing the leg to pull back the femur. Okay, that's its function. If the PCL is not functioning, it means that if I bend this knee and I don't have the PCL, it could almost dislocate on the frontal side. I can show it in this side. So this is a PCL retaining device. If I bend my knee, it could move forward easily because the PCL is not there to capture it. Okay? So that is why people have designed posterior stabilized knee prosthesis. So in this case, if I bend the knee, this post will make sure that my femur is not moving to the front. Actually, it's guiding my femur to the back because it's round. So, And there is a cam here. This is the cam, which is not present here because there's a hole here. And this hole is there to allow the PCL to go through it. Okay. So in case of the posterior stabilized, so we call that a posterior stabilized knee prosthesis, because it stabilizes the posterior cruciate ligament. So the cam captures in the post and it moves the femur backwards. Okay. So there are also different schools again. So in America, most surgeons will use a posterior stabilized knee. And in Europe, most people will use a PCL retaining knee. But of course, the PCL has to be functioning then. Huh? It has to be, the quality has to be checked. Okay. So this is then the functioning of the post cam. So this is what we call the post. And the femoral component has a cam that rotates on the post to make sure that it's rotating backwards. One of the problems with total knee replacements is wear and delamination. So this is a top view of the plastic component. Okay. So there are all kinds of different designs, but you can see here the burnishing and the wear scars of the polyethylene, and it could be even that it's really delaminating. So there are big chunks of polyethylene removed. And you can imagine if you make this very thin, so if you make the plastic very thin, that the contact stress can be very high. So if you make it very thin, it's metal on metal almost, and there is a plastic in between, but the local stress is very high. You can see that in this graph. So this is the thickness of the plastic. If you make it thick, yeah, the stresses will go down. And it also depends on the radius. If the radius is big, the conformity, the stresses are dispersed over a bigger area. So this is a bigger radius, total knee replacement. This is a smaller radius. The smaller radius has higher stresses, of course. Okay. So surgeons typically do not like to go below 8 millimeters of polyethylene thickness. Okay, now the polyethylenes recently have been improved, so they could maybe accept a little bit of smaller thickness. But this is important to think about. So they just cannot put a very thin plastic liner in between. Okay. The wear, of course, also depends on the conformity. Like I just mentioned, the radius is something that will govern the contact stress. So if you have a plastic component, the plastic components are not flat. So they are dished. So this has a curvature, right? So this has a curvature. So this has a radius, but also the polyethylene has a curvature. If they match up exactly, the contact area is maximized. If the polyethylene would be flat, you will have a local stress peak, okay? And the designers can play with that to have higher or lower stress peaks, and that affects the wear also, okay? So if you have a highly conforming joint, okay, so it fits nicely, you have low contact stress, but you have higher constraints because there is less freedom for the femoral component to move around, okay? That means you have high fixation stress. So if this is very much curved and the patient is flexing his leg, the joint cannot seek its own position. So it means that there will be high stresses between the femoral component and the bone because the movement is governed by the articulation, and therefore the stresses will be higher at the fixation, so they will loosen earlier. Okay. If you have a low conforming design, you have high contact stress. Okay, because suppose this is flat, you have very high contact stress, but you have less constraint. So if the patient flexes its leg and it wants to rotate, it can seek its own position. So there is more freedom. So the stresses on the fixation are very low because it can seek its own position. So you have low fixation stress. Okay, so there is a balance to be made. So we want to have low contact stress with low fixation stress. That is the ideal situation. And that is why people came up with mobile bearing designs. Okay, so mobile bearing designs consist of the femoral components, a plastic, but the plastic here can also move relative to the tibial tray. So here you can see an example. This is the tibial tray. This is the plastic. And due to this articulation, so this fits on top of this, it can rotate. So let's see, so instead of having this fixed, it can rotate. And this is then highly polished, and this can rotate. Okay? Yeah? So it means that we can make this now more conforming, because this articulation has then low contact stress, and still it can seek its own position because it can move, because this is highly polished. So that's why they invented mobile bearing knees. Okay? So mobile bearing knees, they have a high conformity and low contact stress, so also low constraints, so low fixation stress, because it can seek its own position. However, you have now two articulating sides. So you could have wear on this side, right, the normal wear, but now you can have also wear on the back side, yeah, because it's rotating around this pin. So you have now a larger surface that could wear. And we haven't been using the mobile bearings for a very long time, so we do not exactly know what the implications are in terms of wear. But this is how why mobile bearings were invented. Okay, so for mobile bearings, the polyethylene insert is not fixed to the tibial component, and the advantage is that you have a large contact area with the femoral components, and the conformity is enlarged, so that gives less wear, and you have a larger mobility, so less risk for loosening. Here you can see an example. So this is a polyethylene, and it can rotate freely to the polish. This is highly polished, and it needs to be very smooth, of course, to reduce the wear between the metal and the plastic. Okay, so this is now highly polished, and this is highly polished, these two metal components. The disadvantage is that you have two bearing surfaces, and it could lead to more wear, but we have to figure it out whether that's actually the case. Now, of course, if you have a knee design that allows a lot of freedom, it means that the soft tissues in the knee are becoming more important. So a mobile bearing knee will never be placed if the lateral ligaments are not very good. So these mobile bearings are typically used for rather healthy individuals. Okay, so because the soft tissue around the prosthesis needs to balance all that rotation, because they have to make sure that the knee is stable, because there is less stability built in the design. Okay. Okay, so we have different total knee replacements. So we have a PCL retaining total knee replacement, and we have a posterior stabilized total knee replacement. We have a fixed bearing knee. So this is a fixed bearing knee because this plastic is fixed to the metal. That's called a fixed bearing knee. And we have a mobile bearing knee so that it can move. And we have a linked total knee replacement. I will get to that as well. These knee replacement components are usually fixated with cement, but there are also on the market cementless fixation. So that means that the backside of this component is made of very rough material, and the surgeon then hammers it on, and then there is going to be ingrowth of bone. So that's how it's going to be fixated. Yeah. And on the tibial side, it's the same. We're going to talk about that tomorrow. Okay, so I told you there is wear, but there is also a problem of delamination, and that is something else than wear. So this is the polyethylene, and this is polyethylene, and this is the femoral component. And if you do a stress calculation, you see that the highest stress is subsurface, so underneath the surface, so not at the surface, but under the surface. In addition, we see that the cracks that we sometimes see in the delaminated polyethylenes are subsurface. So that could be due to the stress levels that are subsurface, the stress peaks, okay? What we discovered maybe around 2000, so 15 years ago already, is that if you sterilize the components, the polyethylene components, you could, on the outside, they looked very nice, but on the inside, you had oxidation. So here you see a cross-section of a polyethylene component, and you see here the oxidated areas, okay? So, and the oxidation makes the implants weaker. So you have a subsurface stress peak together with a weakened material, and that explains why we had delamination. Now all the companies are using other sterilization methods because this was due to gamma sterilization of the polyethylene components. And you can see here an example. So if you use gamma, you see a lot of wide bands. If you use ETO as sterilization, you did not see that. So all the companies are using now other sterilization methods that prevent the oxidation. Okay, so that this does not occur anymore. Another problem in terms of wear is the backside wear. So you can imagine that this plastic has to fit on the metal component in a very good manner. On the other hand, the surgeon needs to lock it into place very easily because he wants to have a choice between the thickness of the polyethylene. He wants to use 8 millimeters, 9, 10, okay? So during the surgery, they tap it on the metal component. So if the locking mechanism, it has to be easy for the surgeon, but it has to create a super stable fixation between the polyethylene and the metal, because what we have seen is during dynamic loading, we saw backside wear. So the wear was not on the articulating, on the articulation, but on the backside of the polyethylene, and that was due to inadequate locking mechanisms. So a lot of companies have dealt with that, so they improved the locking mechanisms. But that is also something very important to look at. Okay. So you have snap fit and all kinds of designs, and I think that now most companies have solved that issue. You can also imagine that from a clinical perspective, not only the design is important, but also the patient aspects are important. So here you can see the damage score on polyethylene, and the heavier the patient, the more wear of what that they found on the polyethylene. So obesity, for example, is really important. So that is really a problem. And what we see now is that people demand more of their implants. So in the old days, we did a total knee replacement and the people were very careful. Now everybody wants to do sports and skiing and basketball and whatever. So it is a little bit similar to this graph. So maybe the person is not obese, but will strain the implant to a high magnitude. And we will see how that will develop. Okay, so a surgical factor could, of course, be that the alignment is not correct and that one condyle is overloaded. Like in this case, the medial condyle is overloaded and the plastic just cannot cope with that. And in general, the alignment should be within 3 degrees. That is the surgeon's target. That this line is compromised by less than 3 degrees. Okay, what we also see, and what is interesting, is that if you look at how the functioning of this knee is that sometimes the knee only is loaded on one side. So, and especially in mid flexion. So if you would stand in extension, both condyles will be loaded. Yeah. And in mid flexion, there is some instability. And in some patients, when people did fluoroscopic measurements, so they can make an X-ray movie, they could prove that there was one condyle loaded. And in fact, in their study, they had 75% of lift-off, they call it. So lift-off on one side. So all the theoretical analysis that we do, of course, we kind of assume that it's loaded on both condyles, but that might not be the case. And that could have big consequences for the wear and the endurance of the implant. So it could lead to catastrophic wear then in that case. Okay, as I mentioned, the people that we treat with these implants, these are condylar implants, and you could have a posterior stabilized or a PCL retaining device. These are still rather healthy in terms of the knee anatomy. Sometimes if you have instability because of the collateral ligaments, both ligaments are not functioning very well, or if there is this flexion contracture, or if there are big deformities, or if there is big bone loss or the bone properties are compromised, the surgeon will opt for a stem extension. Okay, so most implants can be elongated with a stem. So basically the joint will look the same, but the fixation will be extended into the intramedullary canal. You can imagine that this is much more stable. Okay, and in this case, what they do is also they link the articulations. So instead of having the possibility of rotating a little bit in this plane, there is a kind of a hinge here that doesn't allow that anymore, or only to less than 10 degrees or so. So there is a design, so basically there is a pin that links really the femoral component with the tibial component, okay? And we do that only if your whole system of the soft tissue system is not able to provide that stability, because then we have to build it in the components. If we do that, there will be a lot of forces on the fixation, and that's why we need this stem extension to make sure that that fixation, that these implants are fixated very well and they don't loosen. So this is also used in revision cases, for example. Okay, so here you see some examples. And for example, in this case, so sometimes these link prostheses, they fail because so the pin has broken here. So it just fails because of there can be very high forces on these pins. What you see here, for example, is a tumor case. This is a tumor prosthesis. So you can see here the knee. And if you look carefully, this is as long as the femur. And it has here a cone on which we can fit a ball. So this is completely replacement of the femur and the knee joint. Okay, so this is done with an osteosarcoma. If a patient has bone tumor, bone has to be removed, and they replace that with such an implant. These are very costly. An infection is a big problem, of course, and loosening is a big problem. Okay, so if all of these prostheses, they fail, it could be that the surgeon decides, together with the patient, to fixate the whole joint, so you get a stiff joint. And they do that by putting in a nail, an intramedullary nail, as you can see here. So that means that they allow the bones to grow together. Okay, so you remove the cartilage, and make the bony ends fitting so that they can heal together. And it's done by a rod in this case, or plates and screws, or an external fixator. So basically it's a fracture. You create a fracture healing system. And the indication for an arthrodesis is it doesn't happen very often, but it's if total knee replacement is failed, if you have persistent infections, for example, if you cannot use your muscles anymore because everything is deteriorated, if there is a big trauma, if you're paralyzed, and sometimes the patients, after gone through many surgeries, they say, well, make my leg stiff, I'm okay with that, and they decide to do that. Okay, that's it. Thank you very much.